Hello and welcome to The Sleepy Scientist. If you enjoy calm, thoughtful science stories like this one, consider liking the video and subscribing to the channel. It genuinely helps these long, slow explorations find their way to people who might need them. And if you feel like it, let everyone know where you're watching or listening from. A city, a countryside, a quiet room late at night. Wherever you are becomes part of this story, because measurement always begins with position. Tonight's journey is about something so familiar that it often goes unnoticed. Measuring. Measuring time, distance, motion, temperature, light. Measuring the passing of seconds, the width of a room, the age of stars, the shape of the universe itself. These acts feel natural, almost automatic. A glance at a clock, a step forward, a look up at the sky. But there is something quietly strange hidden inside all of this. The universe has no ruler outside itself, no master clock hanging beyond space, no fixed reference point against which everything else can be checked. And yet it measures itself with extraordinary precision. Atoms vibrate at steady rhythms. Light stretches and shifts as space expands. Ancient radiation still carries a record of the universe's earliest moments. Across unimaginable distances and timescales, patterns remain consistent enough to be compared, calibrated and understood. This video is an exploration of how that happens, not as a list of instruments or techniques, but as a story about relationships, about comparison, about how time, space, matter and light quietly serve as reference points for one another, about how measurement works when there is nothing external to measure against. There is no urgency here, no equations to follow, just a slow unfolding of ideas, moving from the familiar to the vast, from everyday clocks to the oldest light in the universe. So wherever you're listening from, allow that place to be your starting point. Because every act of measurement begins somewhere, and from there the universe takes care of the rest. Measurement begins long before numbers appear, before rulers, before clocks, before symbols carved into stone or printed on screens. Measurement exists as a simple act of comparison. One thing placed beside another. One moment judged against the one that came before. One distance felt as longer or shorter than something already known. At its core, measurement is not calculation. It is relationship. Nothing in the universe is measured on its own. A length is only a length because something else is shorter or longer. A moment matters because it follows another moment. Even weight is not an isolated property, but a comparison between mass and gravity, between matter and the pull of a nearby body. Remove the reference, and the measurement dissolves. There is no absolute scale hanging outside reality, no cosmic ruler stretched across existence, no master clock ticking beyond space and time. This is not a limitation of human tools. It is a fundamental feature of how the universe works. Long before mathematics, the human brain evolved to compare. Brighter and dimmer, faster and slower, nearer and farther. Cognitive science shows that comparison is one of the earliest and most basic mental operations, shared across cultures and even across species. Infants can distinguish between quantities without counting. Animals navigate environments by judging distance, duration, and change without ever assigning numbers. The mind does not begin with measurement as calculation. It begins with contrast. Science did not invent this process. It refined it. When early humans watched the sun rise and set, they were not measuring time in units. They were noticing repetition. When the seasons shifted, they were comparing one cycle to another. When shadows lengthened and shortened, They were judging relative position. These were acts of measurement long before they became acts of mathematics. Even now, the most advanced scientific measurements retain this relational core. Consider time. A second is not defined by a universal heartbeat of the cosmos. It is defined by comparing one atomic transition to another identical atomic transition, repeated again and again. The modern definition of the second is based on the regular oscillation of atoms, not because atoms are magical, but because they are consistent. Time is measured by comparing cycles to cycles. There is no standalone second floating through space. Distance follows the same logic. A meter is not meaningful by itself. It is defined through the distance light travels in a fraction of a second, which itself depends on the measured speed of light and the defined duration of the second. Each quantity leans on another. Measurement is circular, but not in a flawed way. It is internally consistent rather than externally anchored. This is why precision does not automatically mean objectivity. A measurement can be extraordinarily precise while remaining entirely relational. A clock can track time to many decimal places, but it is still comparing one repeated process to another. A telescope can resolve distant galaxies with stunning clarity, but those distances are inferred through layers of comparison, not direct contact. Precision sharpens relationships. It does not escape them. Physics makes this explicit. In classical mechanics, motion is always measured relative to a frame of reference. There is no universal state of rest. An object can be stationary on Earth while moving at enormous speed around the Sun, which itself moves through the galaxy, which moves through larger cosmic structures. None of these descriptions is more real than the others. They are comparisons made from different perspectives. Albert Einstein elevated this idea from a practical detail to a defining principle. In the theory of relativity, space and time themselves depend on the observer's motion. Lengths contract, time dilates, simultaneity breaks apart. None of this happens because measurement tools are flawed. It happens because measurement is fundamentally relational. There is no privileged viewpoint from which the universe looks the same to everyone. Quantum physics carries the same message into smaller scales. Properties such as position and momentum are not fixed quantities waiting to be revealed. They are defined through interactions, through measurement itself. The act of comparison is not passive. It participates in what is being measured. This does not mean reality is subjective or imaginary. It means that physical quantities are defined by relationships, not by isolated existence. This relational nature of measurement is not something science hopes to overcome. It is something science works with. Every measurement system ever built relies on internal consistency rather than external truth. Units are chosen, refined, and standardized so that comparisons remain stable across time and space. A kilogram is not heavy because it matches some cosmic mass. It is heavy because it matches other kilograms. A meter is long because it matches other meters. Objectivity in science comes not from escaping comparison, but from making comparisons reproducible. This is why advanced measurement does not free science from its cognitive roots. It formalizes them. Numbers do not replace comparison. They encode it. Instruments do not eliminate interpretation. They stabilize it. Precision does not grant access to an absolute reality. It allows finer distinctions within a relational one. Understanding this prevents a subtle misunderstanding that often creeps into discussions of science. The idea that more precise measurement brings science closer to some final, external truth, independent of observers or context. In reality, precision deepens the web of relationships. It tightens the internal coherence of our descriptions. It does not lift us outside the universe to measure it from afar. There is no outside vantage point. Every clock ticks inside time. Every ruler exists within space. Every detector is made of the same matter it observes. Measurement is the universe examining itself using its own contents through patterns that repeat reliably enough to be compared. This is not a weakness. It is the reason measurement works at all. By recognizing measurement as comparison, it becomes possible to see later techniques not as replacements for earlier ones, but as refinements. Atomic clocks refine astronomical cycles. Spectroscopy refines visual observation. Statistical surveys refine individual measurements. Each layer builds on the same foundational act, comparing one thing to another under carefully controlled conditions. As this story unfolds, scales will grow larger and smaller, the tools will become more abstract, the distances will stretch beyond intuition. But the principle remains unchanged. Nothing is measured alone, nothing is measured from nowhere. Everything is known through relation, and that quiet fact, more than any instrument or equation, is what allows the universe to be measured at all. Long before units existed, the world offered something simpler and more dependable. It offered repetition. Day follows night. Night gives way to day again. The sun rises, reaches a peak, and sinks below the horizon with remarkable regularity. The moon grows bright, then thins away, then returns once more. Seasons arrive, linger, and pass in a slow rhythm that can be felt in temperature, daylight, and the behavior of plants and animals. These patterns repeat whether they are watched or not, and long before anyone counted or calculated, they were noticed. This was measurement in its earliest form, not measurement as quantity, but measurement as timing, not how much, but when the light returns, when the cold eases, when the tides change, when the night sky looks the same as it did before. Reliability mattered more than exactness. A cycle that repeats is useful even if its length is not yet divided into smaller pieces. This is why time becomes the first thing humans truly measure. Distance can be judged, but it resists precision without tools. Weight can be felt, but it changes with effort and fatigue. Time, by contrast, announces itself. It passes whether it is measured or not. And when it passes in regular patterns, it becomes predictable. That predictability is what early measurement was built on. The length of a day did not need to be expressed in numbers to be trusted. The return of the seasons did not require calendars to guide planting and harvest. Knowing that something would happen again was often more valuable than knowing exactly how long it would take. In science, this distinction still matters. Accuracy tells how close a measurement is to some defined value. Reliability tells whether the same result appears again and again. Long before accuracy was possible, reliability was enough. A cycle that repeats allows planning. It allows coordination. It allows memory to turn into expectation. Astronomy quietly shaped this process. The apparent motion of the sun across the sky defines the day. The changing position of the sun along the horizon across the year defines the seasons. The phases of the moon define a repeating cycle that is visible to anyone who looks up regularly. These were not abstract observations. They governed sleeping, hunting, agriculture, navigation, and ritual. The sky became a clock not because it was perfect, but because it was consistent. Of course, these cycles are not identical in length. A lunar cycle does not fit neatly into a year. A year does not divide evenly into days. Even Earth's rotation is not perfectly steady. But these imperfections are subtle. For everyday life, the repetition was close enough to treat as stable. That closeness is the key. Measurement does not begin by demanding perfection. It begins by accepting regularity. Once a cycle is trusted, the next step appears naturally. Division. If the day repeats, it can be split into parts. Morning and evening appear before hours. High sun and low sun come before minutes. The night can be divided by the movement of stars across the sky. These divisions are still comparisons, but now comparisons within a single cycle. One part of the day compared to another part of the same day. Counting enters quietly at this point, not as mathematics in the modern sense, but as ordering. First light, midday, last light, the next day. Counting emerges because repetition invites segmentation. If something happens again and again, it becomes tempting to ask how often, and eventually, how many times. What matters is that counting grows out of cycles, not the other way around. Even today, this structure remains visible. Clocks divide the day, but they still rely on a repeating process. Calendars divide the year, but they still track Earth's orbit. Modern timekeeping may use atoms instead of shadows, but it preserves the same logic. Repetition first, division second, numbers last. This explains why early measurement focused so strongly on time rather than quantity. Time organizes events. It allows cause and effect to be recognized. It makes prediction possible. Knowing when something will happen often matters more than knowing how much of something there will be. In scientific terms, time is the independent variable that quietly underlies almost everything else. Motion is change over time. Growth is accumulation over time. Decay is loss over time. Without a way to mark temporal sequence, even the simplest physical description falls apart. Cycles solve that problem elegantly. They provide a natural reference that does not require invention. The universe supplies the clock. Measurement simply pays attention. This returns to the deeper idea introduced earlier, that measurement is comparison. A cycle is a comparison stretched across time. One sunrise compared to the next. One full moon compared to the one before it. One winter compared to the last. The unit is not fixed yet, but the relationship is clear. This moment matches that one closely enough to be treated as the same. It is important to notice what early measurement does not do. It does not assume absolute beginnings or endings. It does not demand perfect uniformity. It does not require an external standard. Everything is measured relative to what came before. The present is compared to memory. Expectation is formed from repetition. This way of measuring is not naive. It is efficient. It works because the universe is patterned. As science develops, these patterns become quantified. Days become hours. Months become counted. Years are numbered. But the foundation does not change. The reliability of cycles remains the bedrock. Precision arrives later, as refinement rather than replacement. Even modern science depends on cycles at its deepest level. Atomic clocks work because atoms oscillate. Radiation reveals itself through repeating wavelengths. Waves, rotations, and vibrations fill physics from top to bottom. The universe seems especially fond of things that repeat. There is a quiet reason for this. Repetition allows comparison. Comparison allows measurement. Measurement allows knowledge to accumulate. Before units, before instruments, before mathematics, cycles offered a way to know what was coming next. They turned observation into expectation, and expectation into understanding. They showed that time could be trusted, even if it could not yet be counted. And once something can be trusted to return, it can be divided. Once it can be divided, it can be counted. Once it can be counted, it can be measured more finely. The entire structure of timekeeping unfolds from that first simple realization. Things happen again, and in that repetition, the earliest form of measurement quietly takes shape. As long as time was understood through cycles, it remained whole. A day rose and fell, a season arrived and passed, a year returned with familiar signs. These rhythms could be trusted, but they could not easily be adjusted. They were generous in scale and slow in detail, useful for knowing when to plant or rest, but awkward for coordinating action, travel and work that needed to happen at specific moments rather than broad periods. Eventually something subtle changed. Time began to be divided, not because the universe demanded it, but because human activity did. As societies grew larger and more connected, shared rhythms were no longer enough. Markets needed to open together. Ships needed to leave harbours at agreed moments. Religious observances, civic duties, and later mechanical labour required coordination finer than sunrise and sunset could provide. Division brought control. If a day could be split into parts, those parts could be named, ordered, and agreed upon. Morning could be separated from afternoon. Night could be divided into watches. Later, hours emerged, followed by minutes and eventually seconds. Each division added flexibility. Tasks could be scheduled. Journeys could be planned more precisely. People could agree not just that something would happen today, but when during the day it would happen. But division also introduced a problem that cycles alone had hidden. Once time was segmented, irregularities became visible. A cycle can tolerate variation. One day may be slightly longer than another without causing trouble if the goal is simply to know that daylight returns. But once the day is divided into equal parts, those small differences begin to matter. A clock assumes that each division is the same length as the one before it. Nature does not always cooperate. Earth's rotation, which defines the day, is not perfectly steady. It slows and speeds up by tiny amounts due to tidal interactions with the moon, the shifting of mass within Earth's interior, and even large-scale weather patterns. These changes are subtle, but they are real. Over long periods they accumulate. Over short periods they introduce noise. The year has its own complications. Earth's orbit around the Sun is not a neat circle, it is slightly elliptical. Earth also tilts on its axis, causing seasons of unequal length. The time from one solstice to the next is not identical to the time between equinoxes. Even the definition of a year depends on what is being compared. Earth's position relative to the Sun, the stars, or the orientation of its axis. For daily life, these differences are negligible. For precise coordination, they are not. Navigation exposed this mismatch early. Finding latitude is relatively straightforward using the height of the Sun or known stars. Finding longitude, however, requires knowing the time difference between two locations. A navigator must compare local time to a reference time kept elsewhere. An error of even a few minutes can translate into large positional errors at sea. The ocean does not forgive sloppy clocks. This problem became urgent as global navigation expanded. Ships travelled farther, trade networks grew wider, empires depended on accurate positioning. Timekeeping shifted from convenience to necessity. Mechanical clocks were developed to meet this need, but they inherited the same underlying issue. They were still trying to divide a day defined by Earth's rotation into equal pieces. Gears and pendulums could be refined, but the reference itself remained imperfect. The pendulum clock, famously improved by Christian Huygens in the 17th century, brought a dramatic increase in stability. A swinging pendulum provided a regular motion, that could divide time more finely than earlier devices, yet even this depended on gravity, temperature, and mechanical wear. Pendulums change length as materials expand and contract. Friction steals energy. Small disturbances accumulate. Each improvement revealed another layer of inconsistency. This is a pattern that repeats throughout the history of measurement. Refinement exposes limits that were previously invisible. When time was measured by shadows, irregularity did not matter. When time was divided into hours, it began to matter. When minutes were counted, it mattered more. With seconds, it became unavoidable. What emerges is a tension between two desires. One is the desire for continuity, a smooth, repeating reference provided by nature. The other is the desire for uniformity, equal divisions that behave predictably under scrutiny. Astronomical cycles are continuous but not uniform. Mechanical divisions aim for uniformity but depend on imperfect references. This tension explains why timekeeping gradually shifted away from the sky. Not because the sky failed, but because it offered too much variation for the precision now required. The sun and stars are excellent guides for orientation and long-term rhythm. They are less suited for defining identical intervals at the smallest scales humans began to care about. Importantly, none of this requires modern physics to understand. The issue is not relativity or quantum uncertainty. It is simpler and more intuitive. Earth wobbles, orbits stretch, gravity varies slightly from place to place, temperature changes, materials age. Any clock tied to large, complex systems inherits their imperfections. As time became divisible, the demand for something steadier grew. The problem was not how to build better clocks, it was how to choose a better reference, something that repeats reliably, something that is identical wherever it appears, something that does not care about seasons, tides, or geography. This realization did not arrive all at once. It crept in slowly as accumulated experience made the limits of astronomical and mechanical time impossible to ignore. Each correction added to calendars, each adjustment to clocks, was a quiet admission that the underlying reference was imperfect. Dividing time had given humanity control, but it had also removed the comforting blur that cycles once provided. Precision sharpened expectations. Sharper expectations revealed inconsistency. And so, a question began to form, long before the answer was clear. Is there anything in nature that repeats without drifting? Is there a process so stable that its cycles can be trusted not just approximately, but exactly, wherever and whenever it occurs? The sky could no longer provide that guarantee. The Earth itself could not either. The search for a deeper standard was not driven by abstraction, but by practical necessity. Time had become something that needed to agree with itself everywhere. The universe, it seemed, would have to offer a quieter, smaller rhythm. One not tied to planets or pendulums, one hidden beneath the motions of the world, steady enough to anchor all the divisions that had been built on top of it. The solution, when it eventually arrived, would not replace cycles. It would refine them. It would take the idea of repetition to its most reliable extreme. But before that could happen, the problem had to be fully understood. Time could be divided. But the divisions were only as stable as the thing being divided. There is a moment in the history of timekeeping when attention turns inward. After centuries of watching shadows, tracking stars, refining gears and smoothing pendulums, it becomes clear that the problem is not craftsmanship. The problem is scale. The motions of planets and the swing of physical objects are simply too large, too complex, too entangled with their surroundings to serve as perfectly steady references. If time is to be divided cleanly, The reference itself must be smaller, simpler, and more repeatable than anything visible in the sky. That search leads not upward, but downward. Deep inside matter, far below the level of gears or gravity-driven motion, atoms exhibit a remarkable behavior. They change energy in discrete steps, not gradually, not approximately, but in sharply defined transitions. When an atom shifts between two specific energy states, it does so at a frequency that is the same every time, provided the conditions are controlled. This is the foundation of atomic timekeeping. An atomic clock does not measure time by watching something move through space. It measures time by counting how often an atom oscillates as it changes between energy levels. The most widely used standard relies on a specific transition in cesium atoms. That transition occurs at a frequency so stable that it can be reproduced in laboratories around the world with extraordinary consistency. The modern definition of the second is based on this process. A second is defined as the duration of a precise number of oscillations associated with that atomic transition, not because that number is mystical, but because it is repeatable. What makes this possible is quantization. At the beginning of the 20th century, Max Planck introduced the idea that energy is not continuous, but comes in discrete packets. This insight emerged from attempts to understand radiation and heat, but its implications reach far beyond those early problems. Quantization means that certain physical processes are locked into specific values. An atom cannot exist halfway between allowed energy states. It must be in one or the other. That rigidity is exactly what timekeeping needs. Classical systems drift. Pendulums change length. Springs fatigue. Planetary motions shift subtly over time. But an atomic transition, once isolated and controlled, is governed by fundamental properties of matter itself. Every cesium atom is identical to every other cesium atom of the same type. The energy difference between its allowed states does not depend on who is watching, where the atom is located, or what year it happens to be. This is not because atoms are immune to influence. They are sensitive to magnetic fields, temperature, and motion. But those influences can be measured, corrected, and minimized. Once accounted for, the underlying transition remains the same. The result is a reference that does not rely on Earth at all. Atomic time does not care about the length of the day. It does not notice the wobble of Earth's axis or the slow stretching of the year. It ticks at the same rate whether it is placed at sea level or on a mountain, near the equator or close to the poles. In principle, the same atomic clock would function identically on another planet, provided the same physical conditions are recreated. This universality marks a profound shift. Time is no longer anchored to the motion of celestial bodies. It is anchored to the structure of matter. Measurement moves from observing nature's cycles to probing nature's internal rules. Instead of asking how long it takes the Earth to turn, the question becomes how often a specific atomic process repeats. This does not make atomic time more true than astronomical time. It makes it more stable. Stability in this context means reproducibility. Two atomic clocks built to the same standard can be compared and synchronized, even if they are separated by great distances. Their agreement does not depend on shared sunlight, shared gravity, or shared geography. It depends on the fact that atoms behave the same everywhere. This property quietly reshapes the idea of time itself. Time becomes something that can be carried. A ship no longer needs to look at the sky to know the hour elsewhere. A signal transmitted across continents can be time-stamped precisely. Networks of clocks can be synchronized to levels of precision that would have been unthinkable using planetary motion alone. Yet it is important not to misunderstand what has changed. Atomic clocks do not reveal a deeper or more fundamental time flowing beneath the surface of reality. They do not uncover a hidden cosmic beat. They provide a more reliable comparison. They refine repetition to its most stable form. Precision increases dramatically, but the logic remains the same. An atomic clock still measures time by comparison. One oscillation compared to the next, 1 second compared to another second. The difference is that the thing being compared is now extraordinarily consistent. The comparisons accumulate without drifting apart. This is why atomic time is described as precise, not absolute. Precision is the ability to distinguish small differences reliably. Atomic clocks excel at this. They can detect changes in time so small that even slight differences in gravity or motion become noticeable. In fact, atomic clocks are now sensitive enough to measure time dilation predicted by relativity over differences in height of just a few feet. But precision is not the final goal of measurement. It is a tool. Atomic time does not replace earlier concepts of time. It coexists with them. Days and years are still defined by Earth's motion, because those cycles matter for life. Calendars still follow the seasons. Atomic seconds are woven into these older structures, correcting them gently, keeping them aligned. This layered approach is characteristic of modern measurement. New standards do not erase old ones. They sit beneath them, stabilizing what came before. What atomic timekeeping ultimately demonstrates is that the most reliable measurements come from the simplest repeating systems. The fewer moving parts involved, the fewer opportunities for drift. An atom, governed by quantized energy levels, offers a repetition that is both natural and precise. And yet, even here, there is restraint. The goal is not infinite precision. It is sufficient precision, enough to coordinate, to compare, to build further understanding. Atomic clocks provide a foundation upon which other measurements can rest, but they do not stand apart from the rest of physics. They are embedded within it. By turning to atoms, timekeeping reveals a broader pattern that will appear again and again. When measurement becomes demanding, the solution is often to move to smaller scales, where structure is tighter and behavior more constrained. Nature's fine grain offers stability that large-scale systems cannot. This moment marks a turning point. Time is no longer borrowed from the sky. It is drawn from matter itself. The universe, in its smallest constituents, supplies a rhythm steady enough to anchor the vast web of comparisons that follow. Precision has found its footing, not as an end, but as a foundation. Precision can be seductive when a measurement carries many digits, when it repeats with astonishing consistency, when two instruments separated by great distance agree almost perfectly. It is tempting to assume that understanding has arrived alongside accuracy. The numbers feel authoritative, the agreement feels final. But precision and understanding are not the same thing. Precision describes how finely something can be measured, and how reliably that measurement can be repeated. Understanding describes why the thing behaves as it does. One can exist without the other, and in science they often do. Atomic timekeeping offers a clear example of this separation. An atomic clock can measure time with extraordinary precision. The oscillations of atoms repeat so reliably that tiny differences become detectable. Time dilation predicted by relativity can be measured over height differences comparable to a staircase. Two clocks placed a short distance apart will slowly drift out of sync, because gravity affects the passage of time. The measurements are clean, reproducible, and astonishingly exact. Yet this precision does not mean that time itself has been fully explained. Atomic clocks work because atoms behave in a consistent way, not because time has revealed its deepest nature. The clock counts transitions. It does not explain why time flows forward, why it appears continuous in experience, or why it is woven so tightly into the structure of the universe. The measurement is precise. The concept remains open. This pattern is common throughout science. Often measurement advances faster than explanation. New instruments are built, new regularities are discovered, quantities are tracked with increasing accuracy long before the underlying reasons are fully understood. This is not a failure of science, it is how science moves. History offers many examples. Before gravity was explained as the curvature of space-time, it was measured with remarkable accuracy. Planetary motions were predicted using precise tables long before the deeper framework emerged. Long before atoms were understood, chemical reactions were measured, catalogued, and exploited with great success. Measurement carved a reliable path through unknown territory. The same is true here. Atomic clocks reveal how stable certain processes are, but they do not answer every question about time. They tell how long something takes according to a chosen standard. They do not tell why that standard exists or whether time itself is fundamental or emergent. Those are conceptual questions, not metrological ones. Recognizing this difference is essential. Precision does not guarantee truth in a philosophical sense. It guarantees consistency. It ensures that comparisons made today will match comparisons made tomorrow under the same conditions. That reliability is invaluable. It allows science to build structures that do not collapse under their own weight. But it does not close every door. This is why science often measures first and understands later. Measurement provides constraints. It narrows the space of possibilities. It reveals patterns that theories must respect. Without precise data, explanation floats freely, unconstrained by reality. With precise data, explanation must align with what is observed, even if the reason remains elusive. In this sense, precision acts like a map of boundaries rather than a description of terrain. It tells where explanations may go and where they cannot. Atomic timekeeping illustrates this beautifully. It does not tell what time is in an ultimate sense. It tells how time behaves under specific conditions. It tells how it changes with motion and gravity. It tells how consistent certain atomic processes are across space and circumstance. These facts shape theory without exhausting it. There is a quiet humility embedded in this approach. Science does not demand that every measurement come with a complete explanation. It accepts provisional understanding. It allows knowledge to be layered, with some aspects firmly grounded and others still open. Precision becomes a tool for honesty rather than a claim of finality. This humility is not resignation, it is discipline. By separating what can be measured from what can be explained, science avoids confusing reliability with completeness. It resists the urge to fill gaps prematurely. It allows uncertainty to remain visible without undermining confidence in what is known. This attitude becomes increasingly important as measurement improves. As instruments grow more sensitive, they reveal discrepancies that were previously invisible. Slight mismatches appear between expectation and observation. These differences are not failures, they are signals. They point to places where understanding is incomplete, where deeper structure may exist. Atomic clocks, for example, have grown so precise that they can detect effects predicted by theories developed decades earlier. At the same time, they help test those theories, pushing them into regimes where new behavior might appear. Measurement both confirms and challenges. This dynamic relationship between precision and understanding shapes modern science. Precision is not the destination. It is the condition that makes meaningful questioning possible. Without it, explanations drift. With it, explanations are sharpened, constrained, and sometimes overturned. Importantly, this applies beyond time. Once precision becomes the standard, it spreads. Techniques developed for timekeeping influence other forms of measurement. Stability, reproducibility, and comparison become guiding principles across physics. Distance, mass, energy, and motion are all subjected to the same demand for reliable reference. The idea of measuring precisely without fully understanding becomes a feature rather than a flaw. This shift marks a subtle change in perspective. Instead of waiting for perfect theories before trusting measurements, science allows measurement to lead. Instruments become explorers. Data becomes a guide. Explanation follows, sometimes quickly, sometimes slowly. What remains constant is the commitment to clarity. Precision clarifies relationships even when meaning lags behind. It shows how things connect, how they vary, and how they remain the same. It anchors inquiry to the behavior of the world rather than to speculation alone. Seen this way, the extraordinary accuracy of atomic clocks is not a declaration that time has been mastered. It is a demonstration that comparison can be refined to astonishing levels. It shows how far measurement can go without claiming that it has reached the bottom of reality. This distinction will matter again as attention shifts outward. Time was the first quantity to be refined to such precision. But the same questions now arise elsewhere. How precisely can distance be measured when direct contact is impossible? How reliably can space be compared across vast separations? How does precision behave when scale stretches beyond intuition? The lesson carries forward quietly. Exact numbers do not guarantee deep answers. They create a stable platform from which deeper questions can be asked. Precision, when understood properly, is not an ending. It is an invitation. Before measurement reaches outward into space, it learns to stand firmly on the ground. Distance, unlike time, resists abstraction. You can feel how far something is by walking toward it, but that feeling fades quickly once distances grow large. Hills block the view, rivers bend, paths curve. Direct traversal becomes slow, impractical, or impossible. If measurement depended only on walking from one place to another, knowledge would remain tightly bound to immediate experience. Instead, distance is learned through geometry. One of the simplest and most powerful ideas in measurement is the baseline, a known length laid down carefully. It might be a measured stretch of land, a rope pulled taut, or a pair of fixed points whose separation is trusted. Once that baseline exists, distances to other points can be inferred without ever travelling to them. This is where angles enter the story. By measuring the angles between lines of sight from either end of a baseline to a distant object, its position can be determined. This technique is known as triangulation. The name sounds technical, but the idea is deeply intuitive. If you know how far apart your eyes are, and you look at an object from slightly different positions, your brain automatically estimates distance. Surveying instruments formalize this instinct. Triangulation replaces effort with geometry. Rather than crossing a valley, a surveyor measures angles. Rather than climbing a mountain, its height is inferred from its apparent position against the sky. Distance becomes something that can be calculated from relationships rather than conquered physically. This shift is crucial. It allows measurement to move faster than bodies can. Importantly, triangulation depends on reference lengths, not on reaching the target. The baseline must be measured directly and carefully. Everything else builds outward from it. Accuracy at large distances depends entirely on trust in that initial reference. This pattern repeats everywhere in measurement. Small, well-understood lengths anchor larger inferences. Short distances are measured directly. Longer distances are inferred indirectly. The farther out the measurement reaches, the more it relies on geometry rather than contact. This is not a workaround. It is a feature. Even on Earth, direct traversal quickly becomes inefficient. Measuring the width of a river does not require swimming across it. Measuring the distance to a distant landmark does not require hiking to it. Geometry allows space to be measured without being occupied. The same principles guide modern mapping. Global positioning systems rely on time measurements from satellites, but the underlying geometry remains the same. Positions are determined by intersecting spheres defined by distance from known points. Angles, baselines, and reference frames quietly underpin the process. The tools have changed. The logic has not. This continuity matters. It can be tempting to imagine that cosmic measurement demands entirely new ideas, unrelated to everyday experience. In reality, the techniques used to measure the distance between cities and the techniques used to measure the distance between stars share the same skeleton. Both rely on known references, angles, and careful comparison. The scale changes. The geometry does not. Historically, this continuity allowed measurement to extend gradually rather than abruptly. Ancient surveyors used triangulation to map land. Later, the same principles were applied to chart coastlines. Eventually, they were turned skyward. The Earth itself became a baseline, its diameter providing a reference for measuring the positions of nearby celestial objects. This scaling outward is not accidental. It is the only way measurement can remain grounded. If distance measurement suddenly abandoned familiar principles, intuition would be lost. Instead, each extension builds on what already works. The mind carries its understanding forward, even as distances stretch beyond direct experience. There's also a quiet lesson here about limitation. Triangulation depends on angles being measured accurately. At small distances, angles are large and easy to measure. As distances increase, angles shrink. Small errors begin to matter more. Precision must improve to maintain reliability. The method remains valid, but its demands grow stricter. This is why measurement techniques do not disappear as scale increases. They are refined. Better instruments measure smaller angles. Longer baselines increase sensitivity. Errors are reduced through repetition and averaging. The geometry stays the same, but its execution becomes more careful. Even today, the most advanced distance measurements trace their ancestry back to this simple idea. Know one length well, measure angles carefully, let geometry do the rest. Understanding this before leaving Earth is essential. It prevents the impression that cosmic distances are measured by exotic tricks detached from reality. They are measured by extending familiar logic patiently and consistently. The universe is not accessed through mystery, but through careful comparison. By grounding measurement in terrestrial geometry, intuition remains intact. The listener does not step into space unprepared. This same reasoning that measures a field or a valley will soon be asked to measure the distance to stars. The leap is one of scale, not of principle, and that continuity, more than any instrument, is what allows measurement to travel beyond the horizon while keeping its footing firmly at home. Once measurement leaves the ground and turns outward, the first challenge is deceptively simple. How far away are the stars? They do not grow larger as you approach. They do not shift noticeably from night to night. They appear fixed, pinned to the sky like distant marks on a dome. For a long time, this apparent stillness suggested either that the stars were all at the same distance, or that they were unimaginably far away. The answer turns out to be the second one, but discovering that required the careful extension of a very old idea: parallax. Parallax is the apparent shift in position of an object when viewed from two different locations. It is easy to notice nearby. Hold a finger at arm's length and look at it first with one eye, then the other. The finger appears to jump against the background. The closer it is, the larger the jump. The farther away it is, the smaller the shift. This simple effect becomes a powerful measuring tool when the separation between viewpoints is known. On Earth, parallax is used constantly. Surveyors measure distances by observing how landmarks shift when viewed from different ends of a baseline. The principle remains unchanged when the baseline grows larger. For astronomy, the most reliable baseline available is Earth's orbit around the Sun. 6 months apart, Earth occupies opposite sides of its orbit. The separation between these two positions is roughly twice the distance from Earth to the Sun, a span of about 300 million kilometers. That distance is not guessed. It is measured and refined through multiple methods. It becomes a trusted reference length. With that baseline in place, nearby stars can be measured. As Earth moves along its orbit, a nearby star appears to shift slightly against the background of much more distant stars. The angle of that shift is extremely small. For even the closest stars, it is far less than a degree. But with careful observation and patient measurement, it can be detected. From that tiny angle distance follows, the geometry is straightforward. The smaller the shift, the farther away the star must be. If the shift is large, the star is closer. This relationship allows astronomers to calculate stellar distances without ever approaching the stars themselves. Space remains untouched. Geometry does the work. This was the first direct method for measuring distances beyond the solar system. It is worth pausing to appreciate what this means. Parallax does not rely on brightness, color, or assumptions about how stars behave. It relies on geometry alone. It extends terrestrial measurement cleanly into space, a known baseline, measured angles, distance inferred. When stellar parallax was finally detected in the 19th century, it confirmed something profound. The stars were not just far, they were staggeringly far. Even the nearest stars exhibit shifts so small that they require extremely precise instruments to measure. To put this in perspective, the parallax angle of the closest star is less than 1 arcsecond. That is roughly the angular size of a coin seen from several kilometers away. Measuring such angles pushes observation to its limits, and this reveals the method's strength and its weakness at the same time. Parallax works beautifully, but only nearby. As distance increases, the apparent shift shrinks rapidly. Eventually it becomes indistinguishable from measurement noise. Beyond a certain range, no instrument, no matter how refined, can reliably detect the shift. The geometry remains valid, but the signal vanishes into uncertainty. This is not a failure of the idea, it is a consequence of scale. The universe is large enough that even a baseline the size of Earth's orbit becomes negligible beyond a certain distance. Parallax fades not because the stars stop obeying geometry, but because the angles become too small to resolve. Recognizing this limit is crucial. There is a temptation to search for a single, universal measuring technique that works everywhere. Parallax shows why that hope is misplaced. No method scales indefinitely. Each technique has a natural range, determined by the size of its reference and the sensitivity of its measurements. Rather than abandoning parallax when it reaches its limits, Astronomy treats it as the foundation of a layered system. Nearby distances are measured with parallax. Those distances are then used to calibrate other methods that work farther out. Those methods, in turn, are calibrated against still more distant indicators. Measurement becomes a ladder, not a single leap. Parallax occupies the lowest rung. Because it rests on geometry alone, it provides a baseline of trust. Other methods may rely on physical properties of stars or galaxies. Parallax does not. It tells how far certain stars are without asking anything about how they shine or evolve. That makes it invaluable. Even today, parallax remains essential. Modern space telescopes have dramatically extended its reach by observing from above Earth's atmosphere, where distortion is minimized. With careful design, parallax measurements now extend to thousands of light years. But even then, the method eventually gives way to uncertainty, and that is acceptable. Measurement does not demand omnipotence. It demands honesty about limits. Parallax teaches an important lesson that echoes through all cosmic measurement. No single technique can carry the full weight of the universe. Reliability comes from overlap, from cross-checking, from building outward carefully rather than assuming a shortcut exists. It also preserves intuition. By anchoring stellar distances to Earth's own motion, parallax keeps the observer involved. The measurement is not abstract. It depends on where Earth is and where it has been. The observer's position in space becomes part of the measuring apparatus. This idea will return again and again. Measurement is not detached from the universe. It is embedded within it. As distances stretch farther, parallax quietly steps aside, having done its job. It establishes the scale of the nearby cosmos and hands that knowledge forward. The next methods will rely on light itself, on patterns and properties that reach far beyond the reach of geometry alone. But they will do so standing on parallax's shoulders. The universe does not offer its distances all at once. It reveals them in layers, each one measured with the tools appropriate to its scale. Parallax marks the moment when Earth's familiar geometry first touches the stars. Beyond that, measurement must become indirect. And so the story continues, not by abandoning what works, but by extending it, one careful comparison at a time. As distance grows beyond the reach of geometry alone, measurement turns to something that travels freely across the universe. Light. Everything known about distant space arrives carried by light, not because light is special in a mystical sense, but because it is remarkably informative. It moves quickly, it spreads widely, and it interacts with matter in ways that preserve detailed records of what it has encountered. Long after the source itself is out of reach, light continues onward, carrying traces of its origin. At cosmic scales, light becomes the primary messenger. This is a practical necessity. Stars, nebulae, and galaxies cannot be touched, sampled, or manipulated directly. There is no way to probe them with instruments in the way laboratories probe materials on Earth. Distance removes that option entirely. The universe must be studied from afar, using whatever information arrives naturally. Light makes that possible. When light is examined carefully, it reveals far more than brightness alone. It carries structure, it carries pattern, it carries history. One of the most powerful tools for extracting that information is spectroscopy, the study of how light spreads across different wavelengths. When light from an object is separated into its component colors, it forms a spectrum. That spectrum is not smooth. It contains lines, gaps, and patterns that act like fingerprints. These spectral features arise because atoms and molecules interact with light in specific ways. Each chemical element absorbs and emits light at characteristic wavelengths. Hydrogen, helium, oxygen, iron, and countless other elements leave distinct signatures in the spectrum. By identifying these patterns, the composition of distant objects can be determined with surprising confidence. This is not an inference based on appearance. It is a measurement rooted in atomic physics. These same quantized energy levels that make atomic clocks possible also govern how atoms interact with light. Those interactions are consistent everywhere. A hydrogen atom in a distant galaxy behaves like a hydrogen atom on Earth. From this alone, composition becomes measurable across enormous distances. But spectra reveal more than ingredients. The overall shape of a spectrum carries information about temperature. Hot objects emit more light at shorter wavelengths. Cooler objects emit more at longer ones. This behavior follows well-understood physical laws describing thermal radiation. By examining the distribution of light across wavelengths, temperature can be inferred without ever approaching the source. Motion also leaves its mark. If an object is moving toward or away from the observer, the wavelengths of its spectral lines shift slightly. This effect, known as Doppler shift, alters the position of the entire spectrum. By measuring that shift, motion along the line of sight can be calculated. Speed and direction become measurable through light alone. Composition, temperature, and motion are all encoded at once. This is one of light's most remarkable properties. A single observation can reveal what an object is made of, how hot it is, and how it is moving, all without physical contact. No other carrier of information offers such richness at such distance. This capability transforms the nature of measurement. On Earth, measurement often involves interaction. A thermometer must touch what it measures. A scale must bear weight. A ruler must be placed against an object. In space, this approach fails. Interaction is replaced by observation. Observation, in this context, does not mean passive looking. It means extracting structured information from what arrives naturally. Light enables this shift. At cosmic scales, measurement becomes an exercise in inference rather than manipulation. Objects cannot be tested directly. Hypotheses cannot be probed through controlled experiments in the usual sense. Instead, nature runs the experiment, and light delivers the results. This does not weaken science. It reshapes it. Inference demands caution. It requires careful modeling, cross-checking, and restraint. But it also opens doors that direct interaction never could. Entire regions of the universe become accessible through light alone. This accessibility comes with a subtle change in perspective. When measurement relies on interaction, cause and effect are immediate. Push, pull, observe, response. When measurement relies on light, cause and effect are separated by time and distance. The light reaching an observer may have left its source thousands or millions of years earlier. What is measured is not what is happening now, but what happened then. This temporal separation is not a flaw, it is information. The age of light encodes history. By observing objects at different distances, different moments in cosmic time are observed. Space becomes a record of change. Measurement becomes archaeological as well as geometric. Light also allows measurement of things that never emit light directly. Dark regions can be inferred through their effects on surrounding light. Gravitational fields bend light, revealing mass that cannot be seen. Intervening material absorbs specific wavelengths, leaving telltale gaps in spectra. Even the absence of light can be informative. What emerges is a shift from static measurement to dynamic inference. Earlier techniques focused on position and distance. Light adds motion, change, and evolution. Stars are no longer fixed points. They are processes. Galaxies are no longer shapes, they are systems in motion. Measurement expands from where something is to what it is doing. This expansion is not optional. Without it, understanding stalls. Geometry alone can map positions, but it cannot explain behavior. Light bridges that gap. It also reinforces an important constraint. Because measurement relies on what arrives, not on what is chosen, observation must be patient. The universe does not respond on demand. It reveals itself according to its own rhythms. Signals arrive when they arrive. Patterns emerge slowly. Noise must be separated from meaning. This requirement shapes scientific culture. Observation becomes careful, repetitive, and collaborative. Data accumulates over time. Confidence grows through agreement across independent measurements. Once again, comparison lies at the core. Spectra are compared to known atomic signatures. Brightness is compared across wavelengths. Shifts are compared to reference lines. Every inference rests on matching patterns, rather than uncovering hidden objects directly. Light does not deliver answers in isolation. It delivers relationships. These relationships are remarkably consistent. The same physical laws govern light across the observable universe. That consistency allows a spectrum measured in one place to be understood using knowledge gained elsewhere. Measurement becomes transferable. This universality is why light becomes the backbone of cosmic measurement. It does not replace geometry, it extends it. Distance provides context for light. Light provides content for distance. Together they form a framework capable of reaching across vast scales without losing coherence. The moment measurement commits to light, it commits to change. Objects are no longer treated as static markers. They are seen as evolving entities. Their past states arrive encoded in photons that have travelled for ages. Measurement becomes an exploration not just of space, but of time. This transition is quiet but profound. The universe cannot be handled. It cannot be rearranged. It cannot be tested in the usual way, but it can be watched, carefully and patiently, as it tells its story through light. In that watching, measurement becomes an act of listening. Not to silence, but to an ongoing conversation carried by waves that have crossed unimaginable distances. Each spectrum, each shift, each pattern adds a line to the story. From here on, measurement will depend increasingly on inference, on understanding what light can tell and what it cannot, on reading patterns without touching their source. The universe has made its terms clear. If it is to be measured at all, it will be measured by what it sends, not by what is taken. Once light becomes the primary source of information, motion reveals itself in a new way. At everyday scales, motion is easy to see. A car passes by. A person walks across a room. Change happens against a familiar background, and movement is registered directly. But at cosmic distances, this approach fails completely. Stars do not drift across the sky in real time. Galaxies do not slide from place to place while being watched. Even over years, most distant objects appear fixed, and yet they are moving. The universe is full of motion, but much of it is hidden from direct view. To measure it, observation must give way to inference. The key lies not in watching objects change position, but in examining how their light changes as it reaches the observer. This is where Doppler shift enters. The Doppler effect is a change in the observed frequency of a wave when the source and observer are moving relative to one another. It is familiar from sound. A passing siren seems higher in pitch as it approaches and lower as it moves away. The sound waves are compressed in front of the moving source and stretch behind it. Light behaves in the same way. When a light-emitting object moves toward the observer, The wavelengths of its light are slightly compressed. When it moves away, the wavelengths are stretched. The shift is small, often imperceptible to the eye, but it can be measured precisely by examining spectral lines. This matters because those spectral lines provide a stable reference. Each chemical element produces lines at specific wavelengths. When those lines appear shifted from their known positions, the amount of shift can be measured. From that shift, velocity along the line of sight can be calculated. Motion becomes measurable even when position remains unchanged. This is a crucial transition. Distance tells where something is. Motion tells what it is doing. With Doppler shift, velocity becomes accessible without tracking movement across space. A star does not need to move visibly against the background. Its light carries the information. A galaxy does not need to change shape. Its spectrum shifts as a whole. The concept was first described by Christian Doppler in the 19th century, initially in the context of sound. Its extension to light followed as the wave nature of light became clear. What began as an explanation for everyday experiences turned into one of the most powerful tools in astronomy. The implications are far-reaching. Using Doppler shift, astronomers can determine whether a star is approaching or receding. They can measure how fast galaxies rotate. They can detect the wobble of stars caused by orbiting planets, even when those planets cannot be seen directly. Motion that would otherwise be invisible becomes measurable through careful comparison. Once again, inference replaces direct measurement. This shift demands trust in underlying principles. The interpretation of Doppler shift relies on the assumption that light behaves consistently, that atomic spectra are stable, and that the measured shifts are not caused by unrelated effects. These assumptions are tested repeatedly through laboratory experiments and cross-observations. Confidence builds not from a single measurement, but from agreement across many. As with distance, motion measurement reveals its limits. Doppler shift measures only motion toward or away from the observer. Sideways motion produces no shift. This means that velocity measurements are incomplete by themselves. They provide one component of motion, not the whole picture. But even partial information is powerful when combined with other data. Motion measurements transform understanding of structure. A star's speed reveals whether it is bound to a system or escaping it. The rotation speed of a galaxy reveals how mass is distributed within it. The motion of gas clouds traces gravitational forces that cannot be seen directly. Patterns of motion expose the architecture of systems. In this way, motion becomes a probe of invisible structure. Consider galaxies. By measuring how fast stars orbit at different distances from the center, astronomers discovered that visible matter alone could not account for the observed speeds. Something unseen must be contributing to the gravitational pull. Motion revealed what light alone could not. This is a recurring theme. Static measurements describe appearance. Dynamic measurements reveal cause. Doppler shift turns light into a messenger of change. It shows not just where things are, but how they are evolving. Objects become participants in processes rather than points on a map. This dynamic perspective alters how the universe is understood. Instead of a fixed arrangement of stars and galaxies, the cosmos appears as a restless system. Everything moves, everything interacts. Even seemingly calm regions hide complex motion when examined closely. Measurement adapts accordingly. Rather than asking only how far away something is, science begins to ask how fast it is moving, in what direction, and relative to what. These questions are inseparable from understanding large-scale behavior. The importance of this shift becomes clearer as scale increases. At small distances, motion can be tracked visually. At large distances, it must be inferred. Doppler shift bridges that gap. It allows motion to be measured at scales where position remains static to the eye. This prepares the ground for a deeper realization. When Doppler shift is applied not just to individual stars or galaxies, but to the universe as a whole, a striking pattern emerges. Most distant galaxies show their light shifted in the same direction. The shift increases with distance. The farther away a galaxy is, the faster it appears to be receding. This observation will soon demand a radical reinterpretation of motion itself. But even before that conclusion is reached, the method teaches an important lesson. Measurement does not require direct observation of change. It requires reliable signals that encode change. Light provides such signals with remarkable efficiency. Once again, comparison lies at the heart of the process. Observed wavelengths are compared to known reference wavelengths. Differences are measured. Those differences are interpreted as motion. Each step is grounded in repeatable physical behavior. The universe does not need to move in obvious ways to reveal its dynamics. It only needs to send light. And by learning to read the subtle shifts within that light, measurement expands from mapping positions to tracing motion across vast scales. This transition completes a quiet progression. First, space was measured through geometry. Then, matter was analyzed through spectra. Now, motion itself becomes measurable through shifts so small they would be meaningless without careful comparison. From here, the implications grow larger. If motion can be measured everywhere, then patterns of motion may reveal something fundamental about the universe itself. Not just how objects move within space, but how space itself behaves. The tools are in place. All that remains is to follow what the light is already telling us. As motion measurements accumulated, a pattern emerged that could not be ignored. When astronomers measured the spectra of distant galaxies, they found that the light was almost always shifted toward longer wavelengths. This shift was not random. It followed a clear trend. The farther away a galaxy appeared to be, the greater the shift in its light. At first, this was interpreted in familiar terms. If light shifts when an object moves away, then perhaps galaxies were simply flying outward through space. A collection of motions, all pointing outward, might explain the observation. This interpretation fit comfortably within the existing framework of motion inferred through Doppler shift. But as measurements improved, that explanation began to strain. The relationship between distance and redshift was too orderly. It applied in every direction. No matter where the telescope pointed, distant galaxies showed the same behavior. There was no preferred center, no region from which everything appeared to be fleeing. The pattern was universal. This forced a reconsideration of what the shift actually meant. The key insight was that the redshift observed in distant galaxies was not caused solely by motion through space. It was caused by the stretching of space itself. This phenomenon is known as cosmological redshift. As space expands, it carries light along with it. The waves of light are stretched as the distances between points in space increase. By the time the light reaches an observer, its wavelength is longer than when it was emitted. The shift is not due to the source racing away through a fixed background. It is due to the background itself changing. This distinction is subtle but essential. In ordinary motion, an object moves through space. In cosmic expansion, space changes between objects. Galaxies are not so much travelling through the universe as being carried apart by the universe's own growth. Their positions relative to their local surroundings may remain stable, even as the distance between those surroundings increases. This realization overturned earlier models. For much of the early 20th century, many scientists assumed the universe was static. It might be eternal, unchanging on the larger scales. Some theoretical frameworks even introduced additional forces to hold the universe steady against gravity. The idea of a dynamic universe was uncomfortable. Measurement made that discomfort unavoidable. When Edwin Hubble and others compared galaxy distances with their observed redshifts, the pattern became undeniable. Redshift increased with distance. This relationship, now known as Hubble's law, revealed that expansion was not an anomaly. It was a fundamental property of the universe. Crucially, theory did not lead this discovery. Measurement did. Spectra were collected, distances were estimated, patterns were plotted. Only then did theory adjust to accommodate what the data demanded. The expanding universe was not imagined into existence. It was measured into recognition. This is an important example of science at work. Ideas did not shape the data reshaped the ideas. Understanding the difference between expansion and explosion helps prevent a common misunderstanding. An explosion starts from a point and sends material outward into surrounding space. It has a center. Expansion, by contrast, happens everywhere at once. Every region of space stretches relative to every other. From any galaxy, others appear to be moving away. No location is special. No center needs to be identified. A useful comparison is the surface of an inflating balloon. As the balloon expands, points on the surface move farther apart, even though none of them are moving across the surface itself. The expansion is built into the surface. Space behaves in a similar way, though without the need for an external dimension. This analogy is not perfect, but it captures the essential idea. Expansion is not motion through space, it is change of space. Redshift becomes a measure of that change. The amount of redshift tells how much the universe has expanded since the light was emitted. A small redshift means the light left relatively recently. A large redshift means it has been travelling for a long time, during which space has grown significantly. In this way, redshift encodes history. Distance becomes time. Light from faraway galaxies shows the universe as it was long ago. Measurement shifts from mapping positions to reconstructing evolution. Once again, light carries the story. This new interpretation required careful justification. Scientists had to rule out alternative explanations. Could the redshift be caused by unknown interactions with matter? Could light lose energy gradually as it travelled? A so-called tired light hypothesis. These ideas were examined and tested. They failed. The detailed properties of redshift, including how it affects spectra and how it correlates with distance, align with expansion and not with energy loss or scattering. Additional evidence came from observations of the cosmic microwave background and the large-scale distribution of galaxies. Independent measurements pointed to the same conclusion. Expansion was not a convenient explanation. It was the only one that fit all the data. This moment marks a turning point in how measurement informs understanding. Motion inferred through Doppler shift revealed something deeper than velocity. It revealed the behavior of space itself. A tool designed to measure how fast things move became a window into the universe's geometry and history. Measurement had crossed a conceptual boundary. It was no longer just tracking objects within the universe, it was describing the universe as a whole. This shift raised new challenges. If redshift measures expansion, then distance measurements must be reliable. The relationship between redshift and distance depends on knowing how far away galaxies truly are. Errors in distance translate directly into errors in interpreting expansion. Precision now demanded calibration. Not all galaxies are equally useful as distance markers. Their brightness varies, their sizes differ, their properties evolve over time. To turn redshift into a meaningful measure of cosmic expansion, distances must be anchored to objects whose intrinsic properties are understood. This requirement sets the stage for the next layer of measurement. Geometry provided the first distances. Parallax anchored the nearby cosmos. But expansion operates on scales far beyond parallax's reach. To chart it accurately, measurement must rely on objects that serve as standardized references, beacons whose behavior can be trusted across vast distances. Redshift tells how much space is stretched. To translate that stretch into scale, the universe must provide yardsticks bright enough to be seen across its breadth. The realization that space itself expands does not end the story. It deepens it. Measurement has revealed not just motion, but transformation. Not just where things are going, but how the stage on which they move is changing. The universe is no longer a static backdrop. It is an active participant in its own evolution. And as always, this insight did not arrive fully formed. It emerged from careful comparison, from patterns traced patiently through light, from the willingness to let observation challenge expectation. Redshift opened the door to cosmic history. To walk through it, measurement must now become even more careful, even more standardized, and even more deeply layered. Once the universe is understood to be expanding, distance becomes more than a geometric question. It becomes a calibration problem. Redshift reveals how much space has stretched since light was emitted, but it does not by itself say how far away the source is in absolute terms. To translate expansion into scale, measurement needs objects whose true brightness is known. Not how bright they appear, but how bright they actually are. This idea is simple in principle. If two light sources emit the same amount of light, the one that appears dimmer must be farther away. The challenge lies in knowing which sources truly emit the same amount of light. Apparent brightness is easy to measure. Intrinsic brightness is not. This is where standard candles enter. A standard candle is an object whose intrinsic luminosity is known or can be inferred reliably. By comparing how bright it appears to how bright it is expected to be, distance can be calculated. The dimming of light with distance follows a well-understood relationship. Double the distance, and the brightness drops by a predictable amount. What makes this powerful is not the mathematics, it is the trust in the source. If the intrinsic brightness is uncertain, the distance becomes uncertain. If the intrinsic brightness varies unpredictably, the method fails. Standard candles must be objects that behave consistently enough to be compared across vast distances. One of the first major breakthroughs in this area came from variable stars. Certain stars do not shine steadily. Their brightness rises and falls in a regular pattern. Among these, Cepheid variable stars display a remarkable relationship between the period of their brightness variations and their intrinsic luminosity. The longer the period, the brighter the star truly is. This relationship was discovered through careful observation, not theoretical prediction. By studying Cepheid variables in nearby regions where distances could be measured through geometry, astronomers were able to calibrate the link between period and luminosity. Once calibrated, Cepheids became reliable distance indicators. They served as the first true rungs beyond parallax. However, Cepheids have limits. They are bright, but not bright enough to be seen across the full observable universe. As distance increases, even the brightest Cepheids fade from view. New standard candles are needed to reach farther. This is where layered measurement becomes essential. No single method carries the entire burden. Each technique covers a range. Parallax measures the nearest stars. Cepheids extend reach into nearby galaxies. Beyond that, other objects must take over. Type 1. A supernovae provides such a tool. These stellar explosions occur when a white dwarf star reaches a critical mass and undergoes a runaway reaction. The physics of this process leads to a remarkably consistent peak brightness. While not perfectly identical, these explosions are uniform enough that their luminosity can be standardized through careful correction. When such a supernova appears in a distant galaxy, it briefly outshines the entire galaxy around it. For a short time, it becomes visible across enormous distances. By measuring its apparent brightness and comparing it to its calibrated intrinsic brightness, distance can be inferred. Again, calibration is the key. Supernovae are not trusted blindly. Their behavior is cross-checked against closer examples where distances are already known. Corrections are applied for environmental effects and subtle variations. Uncertainties are quantified rather than ignored. This focus on uncertainty is central. Standard candles do not provide exact distances. They provide estimates with known margins of error. Science does not hide these uncertainties. It manages them. Confidence comes not from pretending error does not exist, but from understanding how large it is and how it propagates through calculations. This approach marks a mature stage of measurement. Rather than seeking perfect certainty, science seeks consistency across independent methods. If multiple techniques, each with different assumptions and error sources, converge on the same result, confidence grows. If they disagree, the disagreement becomes a clue rather than a failure. Distance measurement becomes a network rather than a single line. Each standard candle is linked to others through calibration chains. Parallax anchors nearby stars. Those stars calibrate Cepheids. Cepheids calibrate supernovae. Supernovae extend measurement deep into cosmic history. At each step, overlap allows cross-checking. This layered structure is often called the cosmic distance ladder. The name is appropriate. Each rung depends on the one below it. None stands alone. The ladder is not climbed in a single leap. It is ascended carefully, with constant testing of stability. This layered approach also guards against hidden bias. If one method contains an unnoticed flaw, others may not share it. Agreement across methods suggests robustness. Disagreement signals the need for deeper investigation. Measurement becomes self-correcting over time. Importantly, this structure reinforces a theme that has appeared repeatedly. Measurement does not deliver truth in isolation. It delivers coherence. Distances are not known because one object says so. They are known because many independent comparisons align. The universe is measured through consistency rather than authority. Standard candles transform redshift into scale. Redshift tells how much space has stretched. Distance tells how far light has travelled. Together they allow expansion to be mapped quantitatively. Without standard candles, redshift would remain a relative measure. With them, it becomes a tool for reconstructing cosmic history. This reconstruction reveals patterns. The rate of expansion changes over time. Different epochs leave different signatures. Subtle deviations from simple models become detectable. Measurement grows sensitive enough to test ideas about the universe's contents and evolution. But this sensitivity depends entirely on careful calibration. Every standard candle is only as reliable as the chain that supports it. This is why no single method is ever trusted alone. Redundancy is not inefficiency, it is insurance. This philosophy reflects a deeper understanding of measurement. Certainty is not claimed, it is approached asymptotically. Each improvement narrows uncertainty without eliminating it. Each new method adds context rather than replacing what came before. As distances grow larger, this approach becomes indispensable. The universe offers no labels telling how far away things are. It offers signals. Measurement interprets those signals through comparison, calibration, and cross-checking. Standard candles embody this process. They turn brightness into distance, not by assumption, but by carefully managed inference. With these tools, the universe becomes mappable, not as a static picture, but as a structure with scale, depth, and history. Distances link to redshifts. Redshifts link to expansion. Expansion links to time. Measurement now stands ready to move beyond individual objects and toward patterns that span the cosmos. Once distances are established across vast scales, attention can turn from individual beacons to the distribution of matter itself. The map at last begins to take shape. As distance measurements stretch outward and individual objects fade into the background, the universe begins to look different. Not emptier, but more crowded. Stars blur into galaxies. Galaxies gather into clusters. Clusters trace filaments and walls, surrounding vast regions of relative emptiness. At this scale, no single object tells the story. Meaning emerges only when many objects are considered together. Measurement adapts accordingly. Instead of asking how far away one galaxy is, science begins to ask how galaxies are distributed. Instead of focusing on the properties of a particular star, attention shifts to populations. Patterns replace particulars. Averages become more informative than exceptions. This is the birth of statistical measurement in cosmology. Large astronomical surveys are designed not to study individual objects in detail, but to collect data on enormous numbers of them. Millions of galaxies are catalogued. Their positions, redshifts, brightness, and motions are recorded systematically. The goal is not to understand each galaxy, but to understand the structure they form collectively. This approach reflects a fundamental change in perspective. At smaller scales, measurement often seeks deterministic answers. Where is this object? How fast is it moving? What is it made of? At cosmic scales, these questions become less meaningful in isolation. Random variation, local environments, and historical accidents introduce too much noise. Statistics provide a way forward. By averaging over large samples, random differences cancel out. What remains are regularities imposed by underlying physics. The distribution of galaxies reveals the influence of gravity. Clustering patterns reflect the growth of structure for time. Voids and filaments trace the history of expansion and matter distribution. Measurement becomes probabilistic rather than exact. This does not mean it becomes vague. It becomes honest about uncertainty. Instead of assigning a single value to a quantity, science describes a range. Instead of claiming certainty about an individual object, it characterizes the behavior of a population. Probability replaces precision where precision would be misleading. This shift is not unique to cosmology. It mirrors developments in many areas of science where complexity overwhelms simple description. When systems become large and interactions numerous, statistics often provide the clearest insight. In the universe, scale guarantees complexity. No two galaxies are identical. No two regions of space have exactly the same history. Attempting to describe the cosmos one object at a time would be endless and unrewarding. Statistical methods reveal what persists despite variation. Large surveys make this possible. By mapping vast regions of the sky uniformly, astronomers can measure how matter is distributed on the larger scales. They can calculate correlation functions that describe how likely galaxies are to be found near one another. They can identify preferred scales imprinted by early processes in the universe's history. These measurements are not intuitive. They do not correspond to familiar objects. They describe patterns that emerge only when many data points are considered together. This reinforces a broader theme. As measurement reaches farther, direct observation gives way to inference based on populations. Individual data points matter less than their collective behavior. Confidence grows from consistency across samples rather than from detailed knowledge of any single case. Importantly, this does not diminish the value of earlier measurements. Parallax, spectra, Doppler shifts, and standard candles all remain essential. They provide the raw data that statistical analysis builds upon. But once data volume becomes large, the role of measurement shifts from determining individual properties to revealing structure. Structure in this context means arrangement and relation. How galaxies cluster tells how gravity has acted over time. The scale of clustering reveals information about the contents of the universe. The way structure evolves with distance reveals how expansion and matter interact. Statistics turn the universe into a measurable system rather than a collection of objects. This approach also helps manage uncertainty. Individual distance measurements carry error. Individual redshifts may be affected by local motion. Individual brightness estimates may be imperfect. When many measurements are combined, these errors can be quantified and reduced. Patterns emerge that are robust against noise. Measurement becomes resilient. Rather than collapsing under uncertainty, it incorporates uncertainty into its framework. Error bars are not an embarrassment. They are a feature. They define how much confidence can be placed in conclusions and where caution is required. This statistical mindset prepares measurement for its next step. Even the largest surveys observe only a portion of the universe. They sample what is visible. To understand the universe as a whole, a reference is needed that applies everywhere at once, not just where galaxies happen to be. Such a reference exists. It does not come from stars or galaxies. It does not belong to any particular structure. It fills space almost uniformly, offering a background against which all other measurements can be compared. Before that background can be understood, measurement must be comfortable with abstraction. Statistical universes are not intuitive. They require letting go of the desire to picture everything clearly. Instead of imagining objects, the mind must learn to imagine distributions. Instead of focusing on detail, it must attend to pattern. This shift is subtle but essential. It allows measurement to transcend the limits imposed by individual variability. It opens the door to understanding the universe as a whole, not just as a collection of parts. The universe, when seen through statistics, becomes quieter. Individual differences fade. Large-scale order emerges. The noise of particular histories softens into the hum of underlying law. And against that hum, a faint, nearly uniform signal waits to be noticed. Long before stars formed, before galaxies took shape, before any structure could shine, the universe was already filled with light. That light still exists. It does not come from any star or galaxy. It does not belong to any particular place. It arrives uniformly from every direction, bathing space in a faint, almost perfectly even glow. This radiation is known as the cosmic microwave background, and it is the oldest light that can be observed. It is not merely a remnant of the early universe, it is a measurement signal. To understand why, it helps to picture the early universe not as empty space dotted with objects, but as a dense, hot mixture of matter and radiation. In its earlier stages, the universe was so hot that atoms could not exist. Electrons and atomic nuclei moved freely, scattering light constantly. Photons could not travel far without being deflected. The universe was opaque. As expansion continued, the universe cooled. Eventually, temperatures fell enough for electrons to bind to nuclei, forming neutral atoms. When that happened, light was suddenly able to travel freely. The universe became transparent. Photons that had been trapped were released in all directions at once. Those photons have been travelling ever since. As the universe expanded, the wavelengths of that light stretched along with space. What was once energetic radiation became far gentler. Today, it appears as microwave radiation, corresponding to a temperature of just a few degrees above absolute zero. This radiation fills the universe almost perfectly evenly. At first glance, it might seem uninteresting. A nearly uniform glow offers little detail. But measurement thrives on small differences, and the cosmic microwave background is no exception. When measured with sufficient precision, tiny variations appear. These variations are extremely subtle. Differences in temperature across the sky are on the order of 1 part in 100,000. To human intuition, this is almost nothing. To cosmology, it is everything. Those minute temperature differences encode the seeds of structure. In the early universe, matter was not distributed perfectly evenly. Slight differences in density existed. Regions with slightly more matter exerted slightly stronger gravitational pull. Over time, those regions grew denser, eventually forming stars, galaxies, and clusters. The cosmic microwave background captures a snapshot of those initial differences. The warmer and cooler spots in the background radiation correspond to regions where matter was slightly more or less dense at the time the light was released. These patterns are not images of objects. They are measurements of conditions. This distinction matters. The cosmic microwave background is often shown as a mottled map of colours, but it's not a photograph in the usual sense. It does not show locations of stars or galaxies. It shows variations in temperature across the sky. Those variations form a reference grid, a statistical pattern that reflects the universe's state at a specific moment in deep time. That moment occurred when the universe was roughly a few 100,000 years old. In cosmic terms, this is extraordinarily early. Most of the universe's history unfolded after this light was already on its way. When the cosmic microwave background reaches an observer today, it carries information from a time before any familiar structure existed. Measurement here is not about distance alone, it is about history. The background radiation allows measurement of conditions across the entire universe at once. Unlike galaxies, which appear at different distances and therefore at different times, the cosmic microwave background originates from a single era. Every direction observed corresponds to roughly the same moment in cosmic history. This makes it a powerful reference. Because the background radiation is nearly uniform, deviations from uniformity become especially meaningful. Statistical analysis of these variations reveals information about the universe's contents, its expansion rate, and its overall geometry. The patterns are not random. Their sizes, distributions, and correlations follow precise relationships predicted by physical models of the early universe. Acoustic waves in the hot plasma left imprints that can still be detected. The scale of these imprints acts as a ruler embedded in the sky. Once again, geometry enters quietly. By measuring the apparent size of these patterns, scientists can infer whether space is flat, curved inward, or curved outward on large scales. The background radiation does not show curvature directly. It reveals it through pattern distortion. This is measurement by comparison in its purest form. Observed patterns are compared to expected ones. Differences are measured. Those differences are interpreted in terms of geometry and expansion. The cosmic microwave background becomes a reference against which the universe's shape can be tested. Importantly, this measurement spans time as well as space. The background radiation links early conditions to later structure. The same density variations that appear as temperature differences eventually become galaxies and clusters. By comparing early patterns to later distributions, models of cosmic evolution can be tested. This continuity across time is rare. Most measurements capture the universe at a particular moment. The cosmic microwave background connects the present to the distant past in a direct and measurable way. It is not inferred indirectly through complex modeling alone. It is observed. The discovery of this radiation was unexpected. In the mid-20th century, radio astronomers detected a persistent background signal that appeared regardless of where they looked. At first, it was thought to be noise. Only later did its cosmological significance become clear. Measurement once again led understanding, not the reverse. Since then, increasingly precise observations have refined the picture. Satellites designed to measure the cosmic microwave background have mapped its variations across the entire sky. Each improvement in resolution has revealed new detail without undermining the overall consistency of the signal. The background remains nearly uniform, with variations that match theoretical expectations remarkably well. This reliability reinforces confidence in the measurements. The cosmic microwave background does not depend on the behavior of stars or galaxies. It does not rely on standard candles or assumptions about intrinsic brightness. It comes from everywhere and nowhere at once. It provides a global reference. In a sense, it is the universe measuring itself at its earliest accessible moment. The background radiation sets boundary conditions. It constrains what models of the universe can be. Any successful description must reproduce its features. Measurement here acts as a gatekeeper, filtering ideas through observation. As attention turns toward the universe's overall shape and fate, this background becomes indispensable. It anchors large-scale geometry. It provides a baseline for understanding expansion. It links early simplicity to later complexity. Without it, cosmic measurement would lack a unifying reference. What began as a faint glow becomes a foundational dataset. The universe's oldest light does not tell a story in images. It speaks in statistics, patterns, and correlations. It offers a grid rather than a picture, a framework rather than a scene. And within that framework lies a quiet message. The universe has left a record of its beginnings, written not in objects but in subtle variations spread across the sky. By measuring those variations, it becomes possible to test ideas about space, time, and structure at the largest possible scale. Measurement has now reached deep time. From here, it will turn its attention to shape itself. Some of the most important properties of the universe cannot be seen directly. No telescope shows the universe's age. No image reveals its overall shape. There is no edge to photograph, no curvature to point at, no timestamp stamped into the sky. And yet, age and geometry are measured with remarkable confidence. They are inferred. Inference in this context does not mean guesswork. It means drawing conclusions from patterns that must be consistent if a particular description of the universe is correct. Age and shape emerge not from a single observation, but from the agreement of many independent ones. Begin with age. The age of the universe is not measured by looking backward and finding a beginning. It is inferred by combining how fast the universe is expanding now with how that expansion has changed over time. If expansion were constant, age would be simple to calculate. but expansion evolves. Gravity slows it. Other effects speed it up. The universe's history must be reconstructed rather than read off directly. Measurements of expansion rate provide the first ingredient. Redshift data shows how fast distant galaxies are receding as a function of distance. This relationship gives the present-day expansion rate. But extrapolating backward requires understanding how expansion behaved in the past. Here, independent measurements enter. The cosmic microwave background reveals conditions in the early universe. Large-scale structure surveys show how matter clustered over billions of years. Observations of distant supernovae trace how expansion has changed more recently. Each dataset covers a different era. None alone determines the age. Together, they constrain it. When these independent lines of evidence agree, a coherent picture emerges. The age is not observed. It is the value that allows all measured phenomena to fit within a single, self-consistent timeline. Change the age significantly, and tensions appear. Structures would not have had time to form. Expansion histories would conflict with background radiation patterns. Measurement acts as a filter. Geometry follows a similar logic. The universe can have different large-scale shapes. Space can be flat, curved inward, or curved outward. These possibilities are not abstract curiosities. They affect how distances and angles behave across vast scales. Curvature does not mean bending into some external dimension. It describes how geometry works internally. In a curved space, straight lines behave differently. Triangles may not add up the way intuition expects. Large patterns distort subtly. These effects are too small to notice locally. On Earth, space appears flat because curvature, if it exists, is extremely gentle at small scales. Only by measuring across enormous distances do geometric effects become detectable. Once again, inference is required. Patterns in the cosmic microwave background act as a standard reference. The physical size of early fluctuations is known from fundamental physics. By measuring how large those patterns appear on the sky, geometry can be inferred. If space is flat, the apparent size matches expectation. If space is curved, the patterns appear stretched or compressed. This method does not require seeing curvature directly. It requires consistency between predicted and observed scales. Other measurements contribute as well. Large-scale galaxy distributions encode geometric information. The way clustering appears at different distances depends on how space expands and bends. Gravitational lensing, the bending of light by mass, provides additional constraints. Each technique probes geometry in a different way. None of these measurements is decisive alone. What matters is cross-validation. If geometry inferred from background radiation agrees with geometry inferred from galaxy surveys, confidence grows. If gravitational lensing tells the same story, confidence grows further. Agreement across methods suggests that the underlying description is correct, at least within known uncertainties. This is a recurring pattern in cosmic measurement. Consistency is evidence. It is not proof in a mathematical sense, but it is powerful. It shows that many different observations, governed by different physical processes, converge on the same conclusion. This approach reflects a careful philosophy. Science does not claim certainty where none is possible. It claims coherence. A model is trusted because it explains many things at once without contradiction. When contradictions appear, models are revised. This is particularly important for quantities like age and shape, which cannot be checked directly. The universe offers no receipt showing when it began. It offers no grid showing how space curves. What it offers are signals, patterns, and relationships. Measurement interprets those signals by asking a simple question repeatedly. Does this fit with everything else that is known? When the answer is yes, confidence grows. When it is no, attention turns to the discrepancy. This method has proven robust. Current measurements of the universe's age and geometry are supported by multiple independent datasets collected using different instruments, observing different phenomena and relying on different assumptions. The agreement is not perfect, but it is striking. That agreement does not mean the story is finished. Refinements continue. Small tensions remain. New data may adjust values slightly, but the broad picture holds because it is supported from many directions at once. This is measurement at its most mature. Rather than seeking a single decisive experiment, science builds a network of evidence. Each strand reinforces the others. Weakness in one area is compensated by strength in another. The result is a resilient understanding. As measurement reaches this level, another idea becomes unavoidable. If the universe's behavior can be described so consistently across time and space, then certain quantities must remain stable. Some values must act as anchors, ensuring that physical laws do not drift from place to place or era to era. These values are not inferred from geometry or age directly. They are woven into every measurement already discussed. They are the constants of nature. Understanding how constants function and why they are trusted becomes the next step in understanding how the universe measures itself. As measurement grows more precise and more wide-ranging, certain quantities begin to stand out. They appear again and again, woven quietly through every calculation, every comparison, every inference. They do not belong to any single object or location. They do not depend on where or when they are measured. They remain the same. These are the physical constants. It is tempting to think of constants as laws imposed on the universe from outside, fixed numbers handed down by nature dictating how things must behave. But that picture is misleading. Constants are not external rules. They are internal reference points. They are how the universe keeps itself consistent. A physical constant is a quantity that appears unchanged across experiments, environments, and scales. The speed at which light travels in empty space, the strength of electromagnetic interaction, the scale at which quantum effects become noticeable. These values do not fluctuate from place to place. They do not drift over time, at least within the limits of current measurement. This invariance is what makes them useful. Constants are not assumed to be constant because theory demands it. They are treated as constant because measurement shows that they are. Again and again, across laboratories, across continents, across astronomical distances, the same values emerge. That repetition is the foundation of trust. It is important to understand that constants are measured, not derived. Physics does not explain why the speed of light has its particular value. It measures that value and then builds descriptions that remain consistent with it. The same is true for many other constants. They are inputs, not outputs, anchors rather than conclusions. This can feel unsatisfying at first. There is a natural desire for deeper necessity, for an explanation that shows why things could not be otherwise. But measurement does not offer that kind of answer. It offers stability. It offers consistency. It offers a firm ground on which relationships can be compared. In this sense, constants function like rulers built into reality. They allow different measurements to be related to one another. Time can be linked to distance through the speed of light. Energy can be linked to mass through established relationships. Atomic transitions can be compared across laboratories because the underlying constants governing them are the same. Without this internal consistency, measurement would fragment. Each experiment would live in its own isolated world. Results could not be compared. Knowledge would not accumulate. The fact that constants appear invariant is what allows measurement to scale from atoms to galaxies without breaking apart. This invariance also stabilizes inference. When light from a distant galaxy is analyzed, its spectrum is interpreted using the same atomic physics tested on Earth. When time dilation is measured near massive objects, the same constants governing atomic clocks apply. When background radiation patterns are studied, the same fundamental interactions shape their behavior. Measurement works because constants tie everything together. They do not enforce sameness in outcomes. The universe remains richly diverse. Stars differ, galaxies vary, structures evolve, but the rules governing how those differences manifest remain steady. This steadiness is not trivial. If constants varied significantly across space or time, measurement would become ambiguous. A distance inferred in one region might not match a distance inferred elsewhere. Time measured here might not correspond to time measured there. The coherence seen across cosmic measurements would dissolve. That coherence is evidence, not proof of ultimate truth, but strong evidence that the universe is internally self-consistent. Measurement reveals that consistency by relying on the invariance again and again. It is worth noting how quietly constants operate. They are rarely observed directly. Instead, they appear through their effects. A clock ticks steadily. Light arrives with predictable behavior. Spectral lines appear where they should. These regularities are so familiar that they fade into the background. Only when precision increases do constants come into focus. As measurements sharpen, small deviations become detectable. The fact that such deviations are rare and tightly constrained reinforces confidence in invariance. Constants do not merely simplify equations. They hold measurement together. This role becomes especially clear when measurements cross scales. The same constants govern interactions at subatomic levels and at astronomical distances. The physics describing an atom in a laboratory also describes atoms in distant stars. The light emitted by those atoms obeys the same rules. This unity is not imposed, it is discovered. Through measurement, constants act as bridges. They connect timekeeping to distance measurement. They link geometry to dynamics. They allow information carried by light to be interpreted consistently, no matter how far it has travelled. In this sense, constants are not abstract numbers. They are practical tools. They allow the universe to measure itself reliably, because they ensure that the same comparisons mean the same thing everywhere. However, invariance has limits. Constants stabilize measurement, but they also highlight boundaries. They set scales beyond which familiar concepts may fail. Certain combinations of constants define regimes where current theories no longer apply cleanly. At those extremes, measurement becomes challenging not because instruments are inadequate, but because concepts themselves strain. This is where limits enter the picture. Limits are not failures of measurement, they are features revealed by it. They mark regions where existing descriptions reach their edge. Constants point toward these boundaries by defining the scales at which different behaviors dominate. The same invariance that unifies measurement across scales also signals where unification may break down. Understanding constants as internal rulers helps make sense of this tension. They do not promise complete explanation. They promise coherence within known domains. They allow measurement to proceed confidently, while acknowledging that deeper structure may exist beyond current reach. Seen this way, constants are neither mysterious edicts nor arbitrary conveniences. They are discovered reference points, revealed through repeated comparison. trusted because they hold steady. They allow the universe to be measured from the inside without appeal to anything external, and by doing so they quietly outline where measurement remains strong and where it must eventually confront its own limits. As measurement becomes more refined, it eventually encounters boundaries that cannot be engineered away. At first, limits appear practical. Instruments vibrate, signals weaken, noise intrudes. With patience and ingenuity, many of these obstacles are reduced. Better clocks are built, larger telescopes are launched, data is averaged, errors shrink. But beyond a certain point, improvement slows for a different reason. The obstacle is no longer technological, it is physical. Nature itself imposes limits on what can be known at once, how precisely quantities can be defined, and how finely certain features of reality can be resolved. These limits are not signs of failure. They are signs that measurement has reached the structure of the universe rather than the edge of our tools. One of the clearest examples appears at very small scales. In quantum physics, certain pairs of quantities cannot both be specified with arbitrary precision at the same time. Position and momentum are the most familiar case. This is not because instruments disturb the system in clumsy ways, although early explanations sometimes suggested that. It is because these quantities are not simultaneously well defined in nature itself. This principle was articulated clearly by Werner Heisenberg in the early 20th century. The uncertainty principle does not describe a limitation of measurement technique. It describes a property of how physical quantities relate to one another. Uncertainty in this sense is structural. It arises from the mathematical and physical framework that governs quantum systems. The more precisely one quantity is defined, the less precisely its complementary quantity can be. This is not a practical inconvenience. It is a rule that preserves internal consistency. The universe does not hide exact values behind a veil. In some cases, exact simultaneous values simply do not exist. This idea can feel unsettling at first. Measurement is often imagined as uncovering pre-existing facts. A value is thought to be there, waiting to be revealed if the right instrument is used. Structural uncertainty challenges that intuition. It suggests that certain properties are not fixed until measured, and even then only within defined bounds. But this does not undermine science. It protects it. Without such limits, contradictions would arise. Physical descriptions would become inconsistent. Predictions would fail. Uncertainty is not an enemy of knowledge. It is a stabilizing feature that keeps descriptions coherent. Limits also appear at very large scales. There's a maximum speed at which information can travel, set by the behavior of light in empty space. This speed is not a technological bottleneck. It is woven into the structure of space-time itself. No signal, no matter how energetic, can exceed it. This limit preserves causality. Events remain ordered. Causes precede effects. Measurements made in one region cannot instantly influence another. Without this constraint, the universe would become logically unstable. Measurement would lose meaning because sequence itself would collapse. Other limits arise from gravity. As mass and energy concentrate, space-time curves more strongly. Beyond certain thresholds, familiar concepts of distance and time break down. Inside regions such as black holes, current theories struggle to describe what measurement would even mean. The issue is not that instruments cannot survive there. It is that the framework for interpreting measurement is incomplete. These boundaries are not gaps to be filled casually. They mark places where existing theories reach their domain of validity. Recognizing this is a mark of maturity. Science does not assume that every question has an answer in the same language. It accepts that different regimes may require different descriptions. Measurement is powerful, but it is not universal in form. Importantly, these limits preserve consistency rather than threaten it. If quantum uncertainty did not exist, microscopic systems would behave in ways that contradict observation. If information could travel infinitely fast, cause and effect would unravel. If gravity did not impose extreme conditions, the large-scale structure of the universe would look nothing like what is observed. Limits are constraints that make the universe intelligible. They ensure that measurements made in one context remain compatible with measurements made in another. They prevent physical quantities from being simultaneously overdetermined. They protect the coherence of theory across scales. This perspective replaces mystery with realism. Rather than framing limits as failures or secrets withheld, they can be understood as features of the terrain. Just as a map has edges beyond which it does not apply, measurement has domains where its familiar tools must change. There is calm in this recognition. It allows science to proceed without the pressure to explain everything immediately or in a single framework. It encourages careful extension rather than reckless extrapolation. It keeps uncertainty visible without turning it into spectacle. This attitude also clarifies what uncertainty is not. It is not ignorance in disguise. It is not a placeholder for future precision that will remove it entirely. It is not an excuse for vague thinking. Structural uncertainty is precise. It is quantified. It is tested. It is built into predictive models that work extraordinarily well. In practice, this means that measurement remains reliable even when it encounters limits. Atomic clocks still tick predictably. Spectra still reveal composition and motion. Statistical surveys still map structure. Limits define what combinations of measurements are possible, not whether measurement works at all. This balance between power and restraint is one of science's strengths. It allows confidence without arrogance. It allows exploration without overreach. It allows deep questions to be asked without pretending that all answers are already known. As measurement approaches its limits, new tensions emerge. Different methods may suggest slightly different values for the same quantity. Models that work well in one regime may strain in another. These tensions are not signs of collapse. They're signs of opportunity. They point to places where understanding may deepen, where new connections may form, where existing frameworks may need refinement. Importantly, these tensions arise only because measurement has become so precise. Without careful measurement, discrepancies remain invisible. Without limits, contradictions cannot be detected. Precision brings not only clarity, but responsibility. It forces science to confront the edges of its own descriptions. The universe, in this sense, resists being fully compressed into a single picture. It allows itself to be measured, compared, and understood within bounds. Beyond those bounds, it offers hints rather than conclusions. It remains consistent without being completely transparent. This is not a failure of measurement. It is the condition that makes continued inquiry meaningful. By acknowledging limits calmly, science preserves its ability to move forward. It avoids turning uncertainty into drama or certainty into dogma. It treats boundaries as features to be respected rather than walls to be smashed. As measurement continues to refine itself, these limits do not close the story. They focus it. They identify where attention is most needed, where assumptions should be questioned, and where the universe may still be asking questions of us in return. The next step is not to deny these tensions, but to examine them carefully. Some of them resolve, some persist, and some reveal that even in a universe measured with extraordinary precision, a few questions remain delicately, productively open. As measurements grow more precise, agreement is no longer guaranteed. At first, improved precision brings comfort. Values converge. Error bars shrink. Models align neatly with observation. It feels as though understanding is settling into place. But as precision continues to increase, a quieter effect begins to appear. Small disagreements emerge. They are not dramatic. They do not overturn entire frameworks overnight. They appear as slight mismatches between measurements that should, in principle, agree. A value inferred one way comes out a little higher than the same value inferred another way. Two methods, both careful and well tested, drift just far enough apart to be noticed. This is not a breakdown of science. It is one of its most productive moments. Disagreement becomes visible only when measurement is good enough to reveal it. When data is coarse, differences are hidden inside uncertainty. As uncertainty shrinks, tension comes into focus. Precision does not smooth everything out. It sharpens edges. These mismatches often appear where theory is stretched. Models are built to describe broad patterns. They work well within certain regimes. As measurement probes deeper, assumptions that once seemed harmless begin to matter. Simplifications reveal their limits. Effects that were previously negligible become measurable. This is not a sign that the model was wrong. It is a sign that it was incomplete. Consider how multiple measurements of the universe's expansion rate can be made. Some rely on nearby objects and calibrated distance markers. Others rely on patterns imprinted in the early universe and propagated forward through models. Both approaches are grounded in careful measurement. Both are internally consistent. Yet they do not always yield exactly the same result. The difference is small but persistent. It remains even as data improves and analysis becomes more refined. This kind of disagreement does not shout. It whispers, and science listens. Such tensions are not swept aside. They are reported openly. They are scrutinized repeatedly. Independent groups check methods. Instruments are recalibrated. Assumptions are revisited. Sometimes errors are found, sometimes they are not. When disagreements survive this process, they become valuable. They signal that something important may be missing from the current description. Perhaps an effect has been underestimated. Perhaps a parameter evolves subtly over time. Perhaps a deeper connection has yet to be recognized. History shows that many major advances begin this way. Discrepancies in planetary motion led to new understanding of gravity. Unexpected results in radiation measurements pointed toward quantum theory. Small anomalies, carefully measured and honestly reported, have a way of opening doors. What matters is how disagreement is treated. Science does not demand immediate resolution. It resists the urge to force consensus by ignoring inconvenient data. Instead, it allows uncertainty to remain visible. Provisional conclusions are labeled as such. Confidence is adjusted to match evidence, not desire. This restraint is essential. Forcing agreement prematurely can be more damaging than admitting uncertainty. It can lock understanding into frameworks that no longer fit. Honest reporting keeps inquiry flexible. Precision plays a dual role here. On one hand, it exposes disagreement. On the other, it limits how far disagreement can spread. Precise measurement constrains possibilities. Even when models diverge, they do so within narrow bounds. The universe does not permit arbitrary deviation. This balance keeps debate grounded. Disagreement does not mean that anything is possible. It means that something specific is not yet understood. Measurement defines the size and shape of the gap. This is why measurement is always iterative. No result is final. Each new dataset is interpreted in light of existing knowledge. then feeds back into it. Models are refined, predictions are updated, experiments are designed to probe the area of tension more carefully. This cycle does not end. As instruments improve, new disagreements may appear even as old ones resolve. Understanding advances not by erasing uncertainty, but by relocating it to deeper levels. There is a calm realism in this process. Science does not promise a perfectly finished picture, it promises a continually improving one. Measurement does not deliver absolute truth. It delivers increasingly constrained descriptions that work within defined limits. Seen this way, disagreement is not failure. It is evidence that measurement has become sensitive enough to matter. If all measurements agreed perfectly at all times, inquiry would stall. There would be nothing left to test. Progress would become decorative rather than substantive. Tension is the engine of refinement. This perspective also protects science from overconfidence. By treating results as provisional, science remains open to revision without becoming unstable. Strong conclusions are held with appropriate confidence. Weak ones are labelled accordingly. The strength of a claim matches the strength of its support. Measurement provides the discipline that makes this possible. It anchors discussion in evidence. It limits speculation. It ensures that disagreement remains productive rather than chaotic. As more layers of the universe are measured with increasing precision, disagreements are likely to persist. Some will fade with better data. Others will deepen, pointing toward new physics or revised understanding. The important thing is not whether disagreement exists, but how it is handled. Honest reporting, careful cross-checking, and willingness to revise are not signs of weakness. They are the mechanisms by which knowledge remains connected to reality. Measurement, at its best, does not demand certainty. It demands consistency, transparency, and patience. As these tensions accumulate, they invite synthesis rather than fragmentation. Different methods, different scales, and different perspectives must be brought together. Agreement is not enforced. It is constructed carefully from overlapping evidence and shared constraints. In this way, disagreement does not pull understanding apart. It draws attention to the places where deeper coherence may yet be found. As measurement spreads outward and inward at the same time, a quiet requirement emerges. Results obtained at different scales must agree, not perfectly, not trivially, but meaningfully. Measurements of small systems cannot contradict measurements of large ones without consequence. What is learned from atoms must connect to what is learned from stars. What is inferred locally must remain compatible with what is observed across the cosmos. This requirement is known as cross-scale consistency, and it is one of the strongest constraints in all of science. It is also one of the least dramatic. There is no single experiment that enforces it, no decisive observation that declares success or failure. Instead, coherence accumulates slowly as measurements from very different domains line up in ways that were not guaranteed in advance. Consider time. Atomic clocks define time with extraordinary precision using transitions within atoms. That definition must remain compatible with astronomical observations, with orbital dynamics, with the aging of stars, and with the expansion history of the universe. If atomic time drifted relative to cosmic processes, contradictions would appear everywhere. They do not. The same seconds counted in laboratories align with the timing inferred from pulsars, planetary motion, and cosmological models. Minor corrections are applied, but the framework holds. Time measured at the smallest scales connects cleanly to time measured at the largest. This alignment is not enforced by definition alone. It is tested continuously. Distance follows the same pattern. Lengths measured on Earth anchor triangulation. Triangulation anchors parallax. Parallax anchors stellar distances. Stellar distances anchor standard candles. Standard candles anchor cosmological scales. At each step, this same underlying geometry must apply. If distance behaved differently at different scales, the ladder would collapse. Instead, it holds. This does not mean every measurement agrees perfectly. Small discrepancies exist. Uncertainty grows with scale. But the overall structure remains coherent. Distances inferred through independent methods converge within known margins. When they do not, attention focuses on the gap. This is how calibration works across scales. Calibration is not a one-time act. It is an ongoing process of adjustment and comparison. Measurements at one scale are checked against measurements at another. If inconsistencies appear, assumptions are examined. Instruments are rechecked. Models are refined. The goal is not forced agreement. The goal is compatibility. A successful theory is not one that explains everything in isolation. It is one that allows measurements made in very different ways to fit together without contradiction. Coherence becomes the metric of success. This is why measurement is inherently relational. No quantity stands alone. Time relates to distance through the behavior of light. Distance relates to motion through expansion. Motion relates to mass through gravity. Mass relates to energy through fundamental relationships. Each measurement draws meaning from its connections to others. Break one link and tension spreads. This interconnectedness is often misunderstood as circularity, but it is not circular in a flawed sense. It is self-consistent. The universe is not measured against an external reference. It is measured through relationships among its own parts. Cross-scale calibration ensures that these relationships do not fracture as scale changes. An example appears in the study of gravity. Gravity governs the fall of objects on Earth, the motion of planets, the structure of galaxies, and the growth of cosmic webs. Measurements at each scale probe gravity differently. Laboratory experiments test it locally. Observations of stars test it at intermediate scales. Cosmology tests it across the universe. The same underlying description must accommodate all of these. If gravity behaved one way for atoms and another way for galaxies, measurement would reveal that inconsistency. So far, within known limits, it does not. Adjustments are required. Corrections are applied. But coherence remains. This coherence is not assumed. It is earned. It emerges because independent measurements, developed for different purposes and using different tools, align. This alignment is unlikely to occur by accident. It suggests that the universe is internally stable across scales. That stability is what allows measurement to scale at all. Without it, knowledge would fragment. Physics would become a collection of unrelated rules valid only in narrow domains. Instead, descriptions remain connected. Local laws extend outward. Global behavior reflects local rules. This unity is one of science's quiet achievements. It does not announce itself. It is revealed gradually as new measurements fit into existing frameworks without breaking them. When they do break them, the breakage is localized, not catastrophic. The structure bends, adjusts, and continues. This perspective also clarifies how disagreement is handled. When measurements conflict, the goal is not to choose a winner arbitrarily. The goal is to restore coherence. Which assumptions must be revisited to allow alignment? Which corrections must be applied? Which uncertainties have been underestimated? Resolution is guided by consistency, not authority. Calibration across scales is demanding. It requires patience. It requires openness to revision. It requires careful accounting of uncertainty. but it rewards restraint. The more diverse the measurements that agree, the stronger the confidence in the underlying description. This is why large-scale theories are judged by their ability to connect scales smoothly. A theory that explains early universe radiation but fails to match galaxy distributions is incomplete. A theory that explains atomic behavior but contradicts cosmological observation is inadequate. Success is measured not by elegance alone but by integration. Integration is what turns measurement into understanding. As more layers are added from quantum systems to cosmic structure, the universe begins to look less like a collection of separate problems and more like a single, interlocked system. Measurement becomes a way of tracing those interlocks. This returns attention to a central idea. Nothing in the universe is measured in isolation. Every measurement gains meaning through comparison. Every comparison depends on reference points. Every reference point must remain stable across scale if knowledge is to hold together. Cross-scale calibration is the practical expression of that principle. It ensures that a second measured in an atomic clock connects to 1 billion years inferred from cosmic history. It ensures that a meter measured in a laboratory connects to the width of galaxy clusters. It ensures that light emitted by an atom and light travelling across the universe obey the same rules. When this happens, measurement becomes more than bookkeeping. It becomes a test of coherence. The universe passes that test remarkably well, not perfectly, not without tension, but well enough that a single story can be told across scales without tearing. As calibration tightens, the picture sharpens. Measurement no longer feels like a collection of techniques. It feels like a conversation within the universe, where different parts answer to one another in consistent ways. This realization points gently toward a deeper conclusion. If measurement works only through relationships, and if those relationships remain stable across scale, then the universe does not require an external yardstick. It measures itself. When all of these strands are gathered together, a quiet picture comes into focus. Time is measured by atoms. Atoms are understood through light. Light stretches as space expands. Space takes shape through the distribution of matter. Matter evolves over time, guided by gravity and expansion. None of these measurements stands alone. Each depends on the others for meaning. Time would be meaningless without processes that repeat. Atomic transitions provide that repetition, but those transitions are defined by the same physical constants that govern light, energy, and matter everywhere. Atomic clocks work because atoms behave the same way across the universe, not because time exists independently of everything else. Distance would be undefined without time. The meter is tied to how far light travels in a fraction of a second. Astronomical distances are inferred from how long light has travelled and how its properties have changed along the way. Space is measured through time, and time is measured through space. Light, in turn, is not just a messenger moving through space. It is shaped by the space it crosses. As the universe expands, light stretches with it. Its wavelength becomes a record of that expansion. Redshift turns photons into timekeepers, silently counting how much the universe has grown since their journey began. Structure gives light context. Galaxies cluster. Matter gathers into patterns. Those patterns bend light, slow time, and influence motion. The distribution of mass tells space how to curve. Curved space tells matter how to move. Motion feeds back into structure. Everywhere measurement looks, it finds relationships. There is no single quantity that sits at the center, defining all the others. Time does not exist apart from space. Space does not exist apart from matter. Matter does not exist apart from energy. Energy does not exist apart from the constants that govern interaction. Measurement becomes a network. This is not a flaw in our descriptions. It is an accurate reflection of the universe's internal logic. The universe does not come with labels attached. It does not present a master coordinate system. It does not offer an external frame against which everything can be checked. Instead, it offers consistency. The same physical processes occur everywhere. The same constants apply. The same relationships hold. Because of this, comparison becomes possible. Measurement does not require an outside reference. It requires only that internal relationships remain stable. This is what allows the universe to measure itself. When an atomic clock ticks, it does so using processes governed by quantum physics. Those same processes shape the spectra of distant stars. These same spectra reveal motion through Doppler shift. That motion, when examined across many galaxies, reveals expansion. Expansion, when combined with distance measurements, reveals age. Age, when compared to structure, constrains geometry. The loop closes without contradiction. Self-reference, in this context, is unavoidable. Any attempt to measure the universe must be made from within it. There is no external vantage point from which to step back and check the answer. All instruments are made of matter. All clocks tick within time. All observations rely on light that obeys the same rules being studied. Rather than undermining objectivity, this self-reference defines it. Objectivity in science does not mean detachment from the universe. It means reproducibility within it. Measurements are trusted because they can be repeated by different observers in different places, using different tools, and still agree. Agreement does not come from an external arbiter. It comes from internal coherence. This is why calibration across scales matters so much. If time measured in atoms disagreed with time inferred from cosmic evolution, the entire structure would wobble. If distances inferred from geometry disagreed with distances inferred from light, expansion models would fracture. If constants drifted from place to place, measurement would collapse into ambiguity. None of this happens. Instead, the universe behaves as though it knows its own rules. This does not imply intention or awareness. It implies stability. The universe is internally consistent enough to be measured from within, using its own contents as references. This is a remarkable fact, but it is also an understated one. There is no moment where measurement suddenly becomes complete, no point at which the universe hands over a final answer. Measurement continues to refine itself, to expose limits, to reveal tensions, and to invite deeper synthesis. Self-reference does not trap understanding, it enables it. Because measurement is relational, new connections can always be made. As precision improves, relationships become clearer. As scale expands, coherence is tested. As disagreements arise, assumptions are revisited. The universe does not demand perfection from measurement. It demands consistency. This perspective also dissolves a common misconception. Measurement is sometimes imagined as humanity imposing order on a chaotic universe. In reality, measurement works only because order already exists. The universe offers stable patterns. Measurement recognizes and compares them. It does not create them. In this sense, science is less about control and more about alignment. Alignment between clocks and atoms, between geometry and light, between local experiments and cosmic observation. When alignment holds, understanding grows. This view also explains why mystery persists without becoming overwhelming. There are unanswered questions. There are regimes where current theories strain. There are tensions that remain unresolved, but these do not signal collapse. They signal boundaries. They show where measurement has reached the edge of what current descriptions can support. Beyond those edges, New relationships may exist, or existing ones may need reinterpretation. What remains constant is the method: comparison, calibration, cross-checking, restraint. Measurement does not rush ahead of itself. It builds slowly, testing each extension against what is already known. When contradictions appear, they are not ignored. They are held in view, allowed to guide further inquiry. Seen this way, the universe measuring itself is not a poetic metaphor. It is a practical description. Time is measured by matter. Space is measured by light. Light is shaped by space. Structure reveals history. History constrains geometry. Everything participates. There is no need for an external frame because none would add clarity. An outside ruler could not improve internal consistency. An external clock would not tick more meaningfully than those already embedded in atoms and stars. The universe does not require validation from beyond itself. It reveals its structure through relationships that repeat reliably enough to be compared. Measurement is simply the act of noticing those repetitions and organizing them coherently. This realization brings a quiet sense of closure. Not closure in the sense of final answers, but closure in understanding how answers are even possible. The universe is not transparent. It does not explain itself fully, but it is measurable, and it is measurable because it is internally ordered. From the smallest oscillation in an atom to the faint glow of ancient radiation, the same principles apply. Measurement does not stand outside the universe, pointing inward. It arises within the universe, tracing the connections that already exist. And in doing so, it shows that understanding does not require an external viewpoint. It requires patience, consistency, and the willingness to let the universe describe itself in its own terms. As the picture comes together, something important remains deliberately unfinished. Measurement has carried understanding a long way. It has connected atoms to stars, clocks to galaxies, light to history. It has revealed patterns that repeat across vast scales and times. It has shown that the universe is internally coherent enough to be measured from within. But it has not closed the book. There is no final page where uncertainty disappears, no moment where every question resolves into a single answer. This is not a weakness of science. It is a reflection of what science is designed to do. Measurement enables understanding without finality. It tells what can be known reliably, how confidently it can be known, and where the boundaries of that knowledge lie. It does not promise completeness. It promises clarity within limits. Those limits matter. As precision increases, questions sharpen rather than vanish. Knowing a value to many decimal places does not explain why that value exists. Measuring expansion with extraordinary accuracy does not settle what ultimately drives it. Mapping structure across the cosmos does not reveal why the universe has the properties it does rather than others. These unanswered questions persist not because measurement has failed, but because measurement has succeeded. Precision exposes the edges of explanation. It shows exactly where understanding holds and where it thins. It replaces vague mystery with defined uncertainty. That uncertainty is not an absence of knowledge. It is knowledge about what is not yet known. Restraint becomes essential at this point. There is a temptation to fill gaps prematurely, to speculate beyond what measurement supports, to turn unanswered questions into dramatic claims. Science resists this impulse not out of caution alone, but out of respect for coherence. Restraint is a scientific virtue. It allows uncertainty to remain visible without being exaggerated. It allows confidence to be expressed without becoming dogma. It allows inquiry to continue without forcing closure where none is warranted. This restraint does not slow progress. It guides it. By acknowledging what cannot yet be measured or explained, science preserves the integrity of what has been measured. It avoids collapsing different kinds of questions into one. It keeps description, explanation, and speculation in their proper places. This balance is especially important when dealing with the universe as a whole. The universe offers no final experiment, no external check. All measurement occurs within it, using its own contents as references. This means that some questions may always remain open, not because answers are forbidden, but because the structure of inquiry itself has limits. Accepting this is not resignation. It is maturity. Knowledge without finality is still knowledge. In many ways, it is better knowledge. It is flexible, responsive, and honest. It does not pretend to stand outside the universe looking in. It acknowledges its position within. This perspective also changes how progress is felt. Instead of racing toward an imagined endpoint, progress becomes the steady refinement of relationships. Better clocks, clearer maps, tighter constraints, deeper connections. Each improvement sharpens the picture without demanding that it become complete. The universe does not reveal itself all at once. It reveals itself in layers. Each layer builds on the last, sometimes smoothly, sometimes with tension. Some layers fit neatly, others resist integration. Both outcomes are informative. Measurement thrives in this environment. It does not need certainty to function. It needs stability. It needs repeatability. It needs consistency across scales and contexts. When those conditions are met, understanding grows even if final answers remain out of reach. This is why unanswered questions persist alongside extraordinary precision. Precision tells how well something is known. It does not dictate whether everything must be known. The universe appears content to be partially transparent, offering enough structure to be understood, but not enough to be exhausted. There is something quietly reassuring in this. Understanding does not end in closure, it ends in orientation. Knowing where one stands, what is reliable, and what remains open provides a stable footing. Curiosity continues without becoming restless. Wonder persists without becoming confusion. As the pace slows, the focus shifts. Away from techniques, away from instruments, away from models, toward the attitude that makes measurement meaningful in the first place. Patience. Measurement unfolds over time, not just seconds and years, but generations. Instruments improve, ideas mature, errors are corrected. Understanding deepens gradually. There is no urgency built into the universe demanding immediate resolution. The universe has waited billions of years. It is in no hurry. This patience allows perspective. It reminds us that knowledge is not a possession to be completed, but a process to be maintained. Measurement does not conquer the universe, it converses with it. Each observation is a question asked carefully. Each answer arrives with context rather than finality. This way of knowing is not incomplete. It is appropriate. A universe measured from within cannot be reduced to a checklist. It can be described coherently, tested rigorously, and understood deeply without being fully closed. The absence of finality does not weaken understanding. It keeps it alive. As this exploration draws toward rest, that idea can be held gently. The universe does not withhold its secrets out of hostility. It reveals what it can, when it can, through relationships that remain stable enough to be trusted. Measurement follows those relationships patiently, refining them without demanding an end. There will always be more to measure. There will always be better precision, new tensions, and deeper synthesis. But there does not need to be a final answer for understanding to be real. Knowledge without finality is not uncertainty disguised. It is clarity without arrogance, and in a universe as vast and internally ordered as this one, that may be exactly the kind of understanding that fits. To live in this universe is to live inside measurement, not measurement as numbers on a screen or units in a textbook, but measurement as relationship. Time compared to time, distance compared to distance, light compared to light, patterns checked against patterns, again and again, until something stable emerges. What this journey has shown is not a collection of techniques, but a way the universe holds itself together. There is no external clock ticking beyond everything else, no ruler laid alongside space, no vantage point from which the whole can be judged at once, and yet coherence exists. Seconds measured in atoms align with the aging of stars. Distances inferred from light agree with distances traced by geometry. Structure seen today reflects conditions set deep in the past. Measurement works because the universe is internally consistent. That consistency does not eliminate uncertainty. It contains it. Limits exist. Tensions remain. Some questions stay open. But none of that undermines what has been learned. Instead, it defines the shape of understanding, giving it edges that can be trusted. Measurement does not close the universe. It situates us within it. Every observation made, every clock built, every spectrum analysed is part of the same internal dialogue. Matter measures matter. Light measures space. Time measures change. And through careful comparison, those measurements agree often enough to form a shared picture. In that sense, measurement is not something humans impose on reality. It is something reality allows, because its rules repeat reliably enough to be noticed. The universe does not explain itself in words, but it does offer patterns. Measurement is how those patterns are recognized, and this recognition is not detached or cold. It happens through instruments made of atoms obeying the same laws they measure, through minds that evolved inside the same structure they seek to understand. There is no separation between observer and observed that needs to be resolved. Being inside the system is what makes measurement possible at all. This is a quieter conclusion than a final answer, but a more stable one. Understanding does not arrive as completion. It arrives as orientation. Knowing how measurements relate, where they hold, and where they soften gives a grounded sense of place. Not outside the universe looking in, but inside it paying attention. Nothing here demands urgency. Nothing insists on resolution. The universe continues, measured and measurable, consistent without being finished. And within it, understanding continues too, not as a race towards certainty, but as a steady alignment with what holds. To live inside measured reality is simply to notice that alignment, and to let it be enough.